I would start the session now. I hope you're seeing the video of my office. It's the Jenny's screen is. Adriano, can you change the screen to my video?
Actually, you have to do screen sharing with the program.
Yeah. Well.
Great, now it works. Yes.
Okay. Okay. Hello, everybody. Good morning from Tokyo, Japan. This is session 3 of the Quantum Annealing, Adiabatic Quantum Computing Conference, organized at ICTP Trieste. And I'm the moderator of this session, Hidetoshi Nishimori from Tokyo Institute of Technology. And as in the previous sessions, this session is composed of 3 types of talks, 45 minutes, 30 minutes, and 5 minutes. And you can ask questions at the Q&A tab at the end of each longer talks. And for shorter talks for 5 minutes, you can ask questions at the end of the whole bunch of shorter talks as written in the program. So let's start the session. The first talk is by Daniel Lieder. This is indeed a recorded talk that he gave several hours ago. So I ask the operators at ICTP to start, please.
Thank you. Can you see my screen?
Yes, I can see it.
Great. Okay, well, thank you, organizers, and thank you everyone who's tuning in now and who's tuning in later. I would like to tell you about the achievements of the IARPA, QEO, and DARPA QAFS programs, and also talk about the prospects for quantum enhancement with quantum annealing, which is joint work with Elizabeth Crossan on the archive. So it's been a decade since the DWave 1, and it's a time to ask the question, where does quantum annealing stand? Well, we've had numerous studies that have attempted to demonstrate speedups using the DWave processors. And in some cases, we've had examples of constant factor speedups in optimization. That is against all classical algorithms that were tried. And in other cases, we have had claims of a scaling speedup for quantum simulation, speedup against Path-integral Monte Carlo, in the context of geometrically frustrated magnets, where the problem was the scaling of the relaxation time in escape from topological obstructions. So these are very impressive achievements. Now, I will not talk about simulation today. I want to focus on optimization, even though simulation is, of course, a natural and promising application for quantum annealing. Quantum annealing was originally proposed as an optimization heuristic, and that's going to be the focus of this talk. And unfortunately, so far, there has been no study that has demonstrated an unequivocal scaling speedup as opposed to a constant factor speedup in optimization. The closest we got was this work from a couple of years ago, which focused on finding the ground states of a family of planted solution spin glass instances. And in this work, what you're seeing is the time to solution as a function of the problem size. There was a certifiable scaling speedup, certifiable because an optimal annealing time was identified for the DWave 2000Q against simulated annealing with a scaling exponent that was within within the error bars. So this was encouraging, but unfortunately, when you compare against more sophisticated classical algorithms, specifically in this case, spin vector Monte Carlo and simulated quantum annealing, a scaling speedup disappears, a simulated quantum annealing has a scaling exponent that is about a factor of 2 better than the one that we found on DWave. So this type of result begs the question, what is the reason for the lack of the scaling speedup? And there are several possibilities. Perhaps quantum annealing is just an inherently poor algorithm. I'll talk much more about that later. Control errors might be the culprit. Well, it's known that JKS errors have a strong detrimental effect. In fact, they limit the size of devices that can be expected to accurately solve optimization instances if you don't do any error correction or error suppression. And of course, there's decoherence. The single qubit T1 and T2 times for the DWave devices are a lot shorter than the anneal time. And that is often cited as a major problem of quantum annealing, at least relative to the gate model. The importance of the decoherence story is complicated. It depends on whether there's a weak or a strong coupling to the environment, and I'll talk much more about this later as well. But in any case, reducing noise via better engineering is undoubtedly a good idea, and that is borne out when we re-studied the set of problem instances that I just talked about from 2 years ago on the new lower noise DWave 2000Q. Once again computed time to solution as a function of annealing time. And whereas in 2018, the report was for the largest problem size of 2048 qubits, and an optimal anneal time at about 40 microseconds, that's the red dot here. For the same set of problem instances, up to a slight tweak, on the new 2020 low noise machine, we found that the time to solution actually kept going down as a function of anneal time. And no minimum was discernible even at the lowest anneal time of 1 microsecond. So clearly an improvement due to the lower noise characteristics of the new device. So these results with lower noise are encouraging. If we focus on this aspect along with the lack of a scaling speedup in optimization so far, this justifies a reevaluation of the prospects of a quantum enhancement using the traditional quantum annealing approach. And here by traditional, I mean DWave's qubit design. And I think we're going to hear more about that in the talk by Andrew King later in the session. And the idea of adiabatic quantum annealing with forward annealing paths. So for the rest of this talk, I want to talk about two things. One is the emphasis on coherence, which is the approach of the QEO program. And secondly, the critical evaluation or reevaluation of the adiabatic versus diabatic and the forward versus reverse quantum annealing approaches. So let me start with part one, which is the emphasis on coherence. And that is the approach of the QEO program. So what is the QEO program, first of all? It was a program that was started by IARPA officially in June 2017, lasted until February of this year, and actually was replaced by a new DARPA program called QAFS, the Quantum Annealing Feasibility Study. And that is slated to last until August of next year. In both cases, the goal is essentially to evaluate the prospects for quantum enhancement via high coherence and high control quantum annealing. Briefly about the team itself, it's composed of 3 sub-teams, the so-called performer, the government furnished capability or GFC, and the test and evaluation, the TNE. The performer flux team, of which I'm the PI, has about 100 researchers from 10 different institutions. The institutions are listed here. It's an international collaboration. The government furnished capability is at MIT Lincoln Lab, and they do all the fabrication for this program. And the test and evaluation team is centered at NASA Ames, headed up by Eleanor Eiffel, who will also give a talk in this session. So there's a lot to say, obviously, about this program, and I want to focus on a few highlights. So first of all, let me contrast the DWave versus the QEO type flux qubits. And let me focus specifically on architecture and the question of persistent current. So in terms of architecture, in the DWave case, the qubit physical layer is integrated with the classical control layer. In the QEO approach, the qubit physical layer is separated from the classical control layer via a 3D integrated shielded signal routing approach. This is designed to isolate the qubits and hence hopefully increase coherence. And there's a schematic here with the qubit and layer separated from the classical control layer down here through an interposer. In addition, in the QEO case, we have designed the chips so that we have time-dependent control of every qubit and every coupler bias, the H's and the J's, from room temperature. As for persistent current, the DWave qubits have a relatively high persistent current, about 2.5 microamps. But a useful heuristic is that the T1 and the T2 times both scale inversely with persistent current. So you'd expect that a high persistent current will lead to a relatively low coherence time. And just recently, we've had a measurement reported of T1 and T2 of about 16, 17 nanoseconds in the DWave qubits. The QEO so-called capacitively shunted flux qubits, the CSFQs, have a lower persistent current by about a factor of 10. And both T1 and T2 have been measured to be about 100 times larger than the ones reported so far by DWave. So here is an example. The T1 as a function of persistent current. What you're seeing here are the results reported by DWave, by Google, and by QEO. And here's the actual measurement of one of our 4th generation chips with a T1 of 3.5 microseconds. We also measure T2, of course. And so here's an example of the same 4th generation chip with a T2 measured at the symmetric double well or flux insensitive operating point, 130 nanoseconds T2 star. And if you measure at the so-called saddle point, the double flux insensitive operating point, we found a T2 of about 4.5 microseconds. So the summary is the CSFQs so far, at least in the so-called single tier devices without the interposer, have consistently demonstrated a T2 at the saddle point well over 1 microsecond. Assuming that our anneal times are going to be on the order of about a microsecond, this is encouraging. And moreover, when we proceeded to the more advanced double tier, so-called Aridinus generation, the 5th generation, which has 2 different chips bonded together with an interposer, fortunately, the T1 and T2 were essentially unchanged. So that is encouraging. And in fact, we expect T1 and T2 to both improve with further iterations. So where does the program stand now? We are several generations ahead of what I just told you about. We're now on the so-called Hydra generation. That is a 25 qubit chip. It's the world's first 3-tier high coherence 25 qubit quantum annealer. It has 40 couplers. It has individual high bandwidth control of every circuit element, which enables advanced annealing protocols. And it also has state-of-the-art readout using 25 QFPs, quantum flux parametrons, and tunable resonators. We've designed it in 2 different architectures, a square grid and a Kagome lattice. And this is now ready for basic science experiments. It's also on the cusp of being hard to simulate classically at 25 qubits. And we hope that it paves the path towards larger chips, hopefully 100 qubit chips in the not too distant future. Fortunately also, the chip is now cold in the fridge, and we expect it to be ready for science experiments when we finish calibrating it in about a month. Okay, so that is the survey of the QEO program, all I had time for today. And now I want to move on to part 2, which is a theoretical story. And it's about the critical evaluation of the adiabatic versus diabatic and the forward versus reverse quantum annealing approaches. So let me start with something very basic, just so that we're all on the same page. I want to briefly define what I mean by adiabatic quantum computing and quantum annealing in the closed system setting. So consider this the standard model. And AQC is a universal approach to or universal model for quantum computing. As we all know, we start from an easy to prepare ground state, and then we find via adiabatic evolution the final ground state of a general Hamiltonian. In quantum annealing, as I'd like to define it for the purposes of this talk, the focus is on optimization. So it is less general. Now we start from the ground state of a transverse field Hamiltonian, Hx, and we solve the optimization problem defined by an Ising model on some graph via adiabatic evolution using the stochastic Hamiltonian that is a linear combination of the transverse field and the problem Hamiltonian Hz. For the entire talk, I will assume that we're in the stochastic setting, and there will be later talks today in the session about non-stochasticity, and I will not talk about non-stochasticity at all. So now it's worth noting that the possibility of efficiently classically simulating stochastic quantum annealing in the closed system case, that depends strongly on the assumption that the system is at all times in a ground state of the time-dependent Hamiltonian, separated by a non-zero gap from the first excited state. And that begs the question, what happens if we relax this adiabaticity assumption of staying in a ground state and go to a model where we allow diabatic transitions? So this gives rise to two new computational models. One is the generalization of AQC, let's call it DQC. It will also be universal. And DQA, the generalization of quantum annealing. The D obviously stands for diabatic. So these are computational models in which at all times the system remains in a low energy subspace C of the Hamiltonian of width delta and dimension D greater than 1. D is the dimension of the subspace. All right, so schematically, there are some low-lying levels here that comprise the subspace C, and the horizontal axis is dimensionless time S. Transitions are allowed, diabatic transitions are allowed within the subspace, but transitions are suppressed by a gap delta to the orthogonal subspace, C-perp. So that's the diabatic model. And let me make two remarks. One is that in this model, we do not require the initial or the final state to be the ground state. And also, you might wonder, how is this model different from the gate model? And it's different in that we're going to insist that the dimension of the subspace is order 1, whereas in the gate model, the dimension of the space is the full Hilbert space. It's 2 to the n. Okay, so for this model, this diabatic model, what are the conditions under which such diabatic dynamics hold? And this is essentially the subject of the Adiabatic Theorem, even though we're talking about diabaticity. So let me explain. So definitions, as usual, S is the dimensionless time, and capital T is the total evolution time. Let's define the solution of the Schrodinger equation, the unitary U of T in the usual way, and consider the time evolved projection. P0 projects on the subspace C of interest. And let's also consider a projection on the low energy subspace at all times S. Okay, so now we're interested in the difference between this actual evolution, which is P sub T, and the desired evolution. And the adiabatic theorem, due to Janssen, Ruskay, and Seiler, which is stated here, essentially tells us the answer. It tells us that as long as the evolution time is sufficiently large compared to quantities like this, D again is the dimension of the subspace times the norm of the derivative of the Hamiltonian divided by the gap squared at time 0, plus the same at time S, plus some extra terms, which I won't get into. So as long as the time is large compared to these quantities, then the system will stay not just in the ground state, which is the case d equals 1, but in fact within this subspace C that has dimension d. Okay, so this adiabatic theorem is actually a theorem about diabatic quantum computing or diabatic quantum annealing when the parameter d, the dimension of the subspace, is greater than 1. And this is encouraging because it tells us that the conditions for DQC or DQA are actually not harder to satisfy than for AQC or QA. The only difference really is this extra dimensionality factor, which we're going to assume is order 1. So it doesn't really change the hardness of satisfying the adiabatic condition. So now, so far I've talked about the closed system case, but consider also what happens when we have a bath. And let me talk about 4 different types of coherence in the context of adding a bath, of considering the open system. So the first case is actually when there's no bath, and that is just the fully coherent case, unitary evolution. In this case, the full power of universal quantum computing is unleashed. And of course, this is a great model to have in mind, but it's not very realistic. The second model of interest is so-called what I'm going to call the weakly decoherent case. In this case, we will not assume that there is coherence between eigenstates of the Hamiltonian. This is the weak coupling limit, or the WCL. We will assume that energy eigenstates remain coherent superpositions of computational basis states over a time scale longer than the total anneal time t. So no coherence between eigenstates, but coherence within an eigenstate relative to the computational basis. And in this case, quantum advantage is possible by remaining in the ground state. The strongly decoherent case is kind of the opposite limit. Now the energy eigenstates don't remain coherent superpositions over a time scale longer than t. This is the singular coupling limit. In this case, there's no hope of a quantum advantage, and I won't consider this scenario any further. And the final case is motivated by DQA. I'm going to call that C coherent. So now consider coherent superpositions of eigenstates that are maintained inside a low energy subspace C over a time scale longer than t. But again, superpositions with energy eigenstates outside of C may decohere. So in this case, quantum advantage is possible by remaining in C. Right? So clearly, the C coherent case is the generalization of the weakly decoherent case, where we're considering a subspace instead of just the ground state. So because the coherent and the strongly decoherent case are too extreme, I will not consider them any further. So let's focus on these 2 versions of coherence, weakly decoherent and C coherent. And let's combine this with the dichotomy of adiabatic versus diabatic. And I would now like to start filling out this table where we'll be considering the coherent or C-coherent case versus the weakly decoherent case for both forward adiabatic and forward diabatic quantum annealing. And by forward, I mean the traditional scheme of decreasing A as a function of t and increasing B as a function of t. Okay, so let's start filling this out. And then when we're done, I'll talk about the reverse annealing version of this. But before I start filling this out, I just want to say that, of course, coherent or C-coherent is the case where we need some kind of error suppression. And I'm not going to go into it. There are references here which talk about how to enable this C-coherence using error suppression. And that's the subject of another talk. Okay, so with that in mind, that we can implement using error suppression techniques the ability to be in this row, consider first the case of forward adiabatic, coherent forward adiabatic. So the good thing is that we have the Adiabatic theorem in this case with the standard version with the ground state only. And it tells us that provided we evolve the state sufficiently slowly, it will remain close to the instantaneous ground state. Another piece of good news is that there's a provable polynomial speedup, the work by Roland and Cerf on Grover's algorithm. But there is no known example of a provable exponential speedup in this setting. And generally, this setting is efficiently simulable by quantum Monte Carlo. Even though there are some counterexamples associated with topological obstructions and so on, generally it's true that QMC is efficient in simulating this setting of coherent adiabatic, forward adiabatic evolution. So I would conclude that this case has questionable promise. Next, let's talk about weakly decoherent forward adiabatic. So in this case, once again, there is an open system adiabatic theorem. And it tells us that the state for sufficiently long evolution times, the state will remain close to the instantaneous thermal or Gibbs state. So that's good. But there are no known examples of speedup. And once again, this is generally efficiently simulable by QMC. And the reason basically is that classical simulation by QMC involves two ingredients, which are both satisfied here. The Hamiltonian must be stochastic, and the system must be in an equilibrium state, either the ground state, which is the upper left corner here, or a thermal state, which is the lower left corner. So again, I would say this has questionable promise. Next, let's talk about forward diabatic in the weakly decoherent setting. So in this case, well, this first of all is essentially the original DWave setting. And we know that simulating the full open system dynamics is classically intractable for greater than about 20 qubits. And so whatever limited understanding we have of this scenario comes from experiments on the DWave devices and quantum Monte Carlo or spin vector Monte Carlo simulations. And indeed, the simulations correlate well with the experiments that were done on DWave. Now, unfortunately, as I've already mentioned earlier, QMC is efficient or scales even better, or scales better, even with thousands of qubits, as illustrated in this work. So that's not encouraging, although it should be mentioned that control noise could be playing a major role here. Also, there are no known examples of scaling speedups in this case, so I would say this too has questionable promise. So it's not looking good so far. But let's talk about the upper right corner now. So coherent or C-coherent forward diabatic. First of all, this is a scenario that enables universality. We know that AQC and excited states of stochastic Hamiltonians can be universal. We know that even a time-independent stochastic Hamiltonian suffices for universality via mapping to quantum walks. And we also know that simulating the full closed system dynamics in this case is classically intractable for greater than about 40 qubits. There are also numerical examples of a speedup over the adiabatic coherent case. So contrasting forward adiabatic and forward diabatic, there's an advantage being in the upper right versus the upper left. And so one example is where DQA solves oracular problems with a scaling speedup over the adiabatic case. And specifically, this is known for qubit permutation symmetric problems, where C is the symmetric subspace with respect to qubit permutations. And so the cost function in this case is defined over bit strings, with the function here being only of the Hamming weight of a bit string. So one example is the so-called fixed plateau problem. The ground state is obviously where the Hamming weight is 0, or the all 0 bit string. And if you compare adiabatic quantum annealing versus DQA, what you find is that the time to solution for the adiabatic case scales like square root of n, the number of qubits. But remarkably, in the DQA setting, the time to solution is constant. It's independent of n. And that happens via a so-called diabatic cascade, which is a sequence of avoided level crossings, which is shown here for the fixed plateau problem. You can clearly see this line of avoided level crossings that eventually takes the system back down to the ground state. So that's encouraging. Also very encouraging is recent work on optimal QAOA, which is, turns out optimal QAOA is a bang, anneal bang type protocol, which is very DQA-like. And I think we're going to hear a lot more about that in Lucas Brady's talk later in this session. So all in all, this upper right corner here seems to be promising. So to summarize, the verdict for the forward quantum annealing case is that coherent forward adiabatic is promising, but the other forward annealing cases face some serious challenges. Okay, so that's the forward annealing case. Now, what about reverse annealing? So for reverse annealing, let me just define the model first. I'm going to go through the same exercise of trying to fill out the table with reverse having replaced forward. So here's a schematic of a schedule where in reverse annealing, we start at s equals 1, go down, and then back up again. Whereas in forward, we just go from s equals 0 to s equals 1 with the possibility of a pause in the middle. So more generally, reverse annealing is a family of protocols that start from the ground or excited state of a diagonal Hamiltonian. They anneal to an off-diagonal Hamiltonian and then end with a diagonal Hamiltonian. And here are two important examples. One is so-called adiabatic reverse annealing, or ARA. And here the Hamiltonian is a combination of a diagonal HZ1, starts there, ends with HZ2, possibly different diagonal Hamiltonian. And in the middle, there is an off-diagonal component. And this is adiabatic, and that means we initialize in the ground state of HZ1. Then there's also iterated reverse annealing, or IRA. And here we start from a diagonal Hamiltonian and reverse anneal to an off-diagonal Hamiltonian. That's a combination of HZI and a transist field. But optionally pause, and then forward anneal to a potentially new diagonal Hamiltonian, HZI plus 1. We can iterate this. And for every I, we initialize in the ground or excited state of HZI. And this protocol is implementable on DWave. Okay, so now let's start to fill out the table. And let me start with the upper right corner. This is the case for which we have the first example of an exponential speedup in quantum annealing, except now I want to highlight that it is really in the setting of reverse diabatic quantum annealing, assuming C coherence. And the example is the well-known glue trees problem. I'm sure almost everyone here is familiar with it. You see this as a type of adiabatic reverse annealing between two diagonal Hamiltonians, H0 and H1. And in the middle, the Hamiltonian has this term, which is the adjacency matrix of the glue trees graph. What's remarkable about this problem is that it has a ground state and a first excited state, which are separated by at first a polynomially small gap, then an exponentially small gap. This is where diabatic transition happens. Again, a polynomially small gap. Again, an exponentially small gap where a second diabatic transition down to the ground state happens, and then a polynomially small gap. And the subspace C in this case is just the two lowest energy eigenstates. So it's been well established that this model exhibits an exponential quantum speedup, essentially for the problem of locating a path from the entrance to the exit. Okay, what happens when we, and of course I should say this means that this model is promising, the fact that we have a proof of an exponential speedup. Now what happens when we introduce a bath in this case? You can read about the details in our preprint, but it turns out that this still works for a sufficiently low temperature. So in particular, let's say that we want to prepare at all times the Gibbs state with inverse temperature beta. And let's assume that the temperature has this scaling given here. In that case, the distance, the trace norm distance between the final Gibbs state and the final ground state can be made arbitrarily small. So the story is, you see the 1 over n to the 4th here. As long as the temperature scales like 1 over n to the 4th, then the thermal Gibbs state is arbitrarily close to the final ground state. Right, so we don't need to do this at 0 temperature. Well, we can work in an appropriate weak coupling limit, and it still works. So we have an exponential quantum speedup in an Annealing setting at sufficiently low temperatures for this model. In addition, of course, simulating the full open system dynamics in this case is classically intractable. And so with these observations, I would consider this reverse diabatic weakly decoherent case also promising. Next, we have the very recent result by Matt Hastings on a super polynomial quantum classical separation for the reverse adiabatic case. And I'm sure we're going to hear much more about this from Matt in session 3 today. But just very briefly, I would call this problem large cycle detection. Essentially, it's framed similarly to glued trees, where now the adjacency matrix is one of a different graph. And the computational problem is to determine a global property of this graph, namely, is a large cycle present? And what Hastings showed is that classically this takes at least n to the log n oracle queries, whereas the adiabatic quantum algorithm solves this problem in polynomial in n time. Again, this is done in the reverse annealing setting. There are some caveats. Both this algorithm and Grover and glue trees require many body interactions. So they're more existential than implementable. They're not suitable in particular for quantum annealing with local Hamiltonians. So one might wonder what happens if you do impose the condition of a local Hamiltonian. And in that case, consider the Pspin model with adiabatic reverse annealing. So the model is one where the cost function is of this form. It's a trivial problem, computationally speaking. You can immediately see the answer. The ground state is the all zero state. But this is a model that is known to exhibit quantum phase transitions. And so it's interesting to try to see if the reverse adiabatic version can do better than the forward adiabatic version. And indeed it can. Let's introduce a diagonal Hamiltonian, an initialization Hamiltonian of this form, where the epsilon i's are chosen as plus or minus 1 at random, with C the probability of epsilon I being +1. And what you can show then through a mean field calculation, so this is not numerical, this is analytical. In the S lambda plane, S and lambda are the two annealing schedules here. You can show that for small c, small probability of epsilon being 1, there's a continuous line of first order phase transitions. But as you increase c, this line breaks, and wherever there's no first order phase transition, the white space is second order phase transitions. In this case, first order phase transitions, as they usually do, correspond to an exponentially small gap. Second order transitions correspond to a polynomially small gap. So it makes sense to try to find a path like this purple one here that avoids, let's say for c equals 0.8 or 0.9, it avoids the line of first order phase transitions. This is not something you can do with standard forward quantum annealing, because then lambda is fixed at 1. And all you can do is go straight up the s-axis. In this case, you always cross the first order phase transition. So this is about avoiding a first order phase transition, finding a path that navigates around it by introducing an additional parameter in the adiabatic reverse annealing setting. And if you do this, then you can demonstrate numerically that the time to solution as a function of problem size goes from exponential in the forward quantum annealing case to polynomial in the reverse quantum annealing case. So that's an exponential speed up relative to forward adiabatic quantum annealing. The caveat here is that this requires a good initial guess, C, which is close to the ground state. And so it's not clear how well this generalizes to hard optimization problems. Nevertheless, I would say that in light of these results, the coherent or C-coherent reverse adiabatic case is promising. And that leaves us just with the weakly decoherent reverse adiabatic case, where we don't have too many results. We have some numerical results on an improvement that's possible over the closed system version. And I think I'm starting to run out of time, so I'll skip the details here. I'll just say that it's numerically possible to demonstrate an improvement over closed system. You see the success probability in a closed system Pspin model simulation with iterated reverse annealing versus the open system. Same problem, but now coupled to a bath, and you see how the success probability has increased as a function of the inversion point, the point at which we flip the direction of the A and the B anneal schedules. So what's going on here is that relaxation helps. That's the bottom line. And that has also been shown in a study on DWave, where forward annealing was compared to reverse annealing. And without getting into the details here, you see the residual energy as a function of the pausing point. And for different initializations, first of all, if you just do regular forward annealing, that's the dash curve. But if you do reverse annealing, iterated reverse annealing in the terminology I introduced earlier, depending on what your initial state is, if you start in the ground state, you do better than the forward annealing protocol. If you start in a higher state, then you don't. But iterated reverse annealing with an initial state that is the ground state itself does better than forward annealing for the same problem studied here, which was a 12-qubit small gap problem. However, it is the case that we haven't really changed the fact that quantum Monte Carlo is expected to be efficient in this setting, and that, of course, leads to some skepticism. So I would not rule out this case. I think it's worth further exploration because we don't have enough answers yet. So that's it. Let me now present you with the completed table, and you see that overall the reverse annealing approach, and specifically the reverse diabatic approach, has the most green in it. That's the last column. So I think that if we're going to focus our efforts on finding better ways to do quantum annealing and ask ourselves what the prospects are for a quantum enhancement using stochastic quantum annealing, that seems to be the most promising corner to focus on, with some additional possibilities elsewhere. Okay, thank you for your attention.
Thank you.
Okay, thank you very much. This was the recorded talk, but it seems that the speaker, Professor Daniel Lieder, is online, and he may be able to answer questions, if any. Am I right, Daniel?
Yes, I'm here.
Okay.
Available to answer questions.
Thank you. So if you have questions, type in your question in the Q&A tab. Or if you're a panelist, a speaker, you can ask questions directly by turning on your voice. May I myself ask you a small question? You, in your C-coherent case, you seem to have assumed that there are a bunch of states near the ground state which are well separated from the rest. And is this a generic situation? How general is your result?
No, I don't expect that to be a generic situation at all. However, we do know some important examples where that is the case. And looking for a problem that has a quantum speedup is always looking for a needle in a haystack. So it shouldn't surprise us that the generic case does not have these nice features, but we should be looking for those cases that do.
Okay, I understand. Are there any further questions from the audience? If not, since the time is just 45 minutes after the start, we may switch the talk to the next speaker, Dr. Hastings. Are you ready?
Yeah, hi.
Okay, please go on.
Okay, good. Let me start sharing. Sorry, one sec. All right, okay, good. Uh-oh, sorry, I technical, yeah, I think I might have hit the wrong thing here. I did hit the wrong thing, I think, sorry. Sorry, I shared the wrong thing there. Let me try again. Okay, good. So please, I would like to get questions. I'm not sure if I'm going to be able to see the chat window during this, so maybe someone could interrupt with voice if there's questions, because I've given, longer versions of this talk online, which have been recorded. So if it's just a matter of giving the talk, you can certainly just watch those. So please give questions. So this talk is going to be about the computational power of the adiabatic algorithm with no sign problem, of adiabatic quantum computing with no sign problem. So what we imagine, right? We imagine, hopefully everyone can see, there we go. We imagine some path of Hamiltonians like H sub s, there'll be some parameter s, which is going to be a linear combination of two different terms. There'll be a driving term, 1 minus s times x, where x will be, say, some Pauli transverse field. It's the sum of x sub I on a bunch of qubits, plus s times some objective function, h sub z. And at s equals 0, everyone knows, assume in this audience, that the ground state is easy to repair. At s equals 1, this might encode the solution of some optimization problem. And if the gap does not go too small, as you go from s equals 0 to s equals 1, then you'll succeed in going from the initial easy to repair state to the ground state of your optimization problem. So we can ask, what is the computational power of this model of adiabatic quantum computing? So if you restricting, let's say, to the case in which the gap between the ground and first excited state is only polynomially small, so you can do the path in a polynomial time, ignoring all realistic questions about excitation to higher states, decoherence, and so on. If you don't impose any restrictions on these two Hamiltonian terms, x and h sub z, and they're just arbitrary local Hamiltonians, such that the first one you can prepare efficiently, then the answer is completely clear. This is equivalent in power to standard quantum computing. This is an old result of Aharonov and collaborators from a long time ago, I think more than 15 years ago. But you might wonder about the special case. What happens when we impose this condition that there is no sign problem? What we mean in general for no sign problem, to say a Hamiltonian is no sign problem, people use the word stochastic, but I just personally, it sounds a little weird to me, is that all the off-diagonal matrix elements of the Hamiltonian are non-positive. So if you have some h sub ij, and now I'm going to use the subscripts to denote matrix elements of the Hamiltonian some preferred basis, these are all less than or equal to 0. And in this case, you want it to be true for all s in this interval. S goes from 0 to 1. Now, once you impose this condition that there's no sign problem, the problem gets easier to treat. For one thing, if you just ask for the problem at a specific value of s. You just say, okay, a particular Hamiltonian with no sign problem, ignoring all this question of adiabatic evolution and so on, just give a particular Hamiltonian with no sign problem. You can ask about its computational power. And this has been, there's an algorithm that's very successful often in practice, quantum Monte Carlo, at simulating this. It can get stuck. It's a Markov chain algorithm, and it can get stuck like any Markov chain algorithm can. But work of Terhal, Bravi, and others, I don't remember all the others, have shown that this is some computational class. It's either MA or AM, I forget exactly, but it's basically it's believed under some de-randomization assumptions to be the same as NP. It's a little bigger than NP, but it's believed, under de-randomization assumptions. It includes NP. It's believed to be the same under some de-randomization assumptions. Believed not to be quite as big as QMA. So now you might ask the question, well, what if we combine these two restrictions? If we combine this restriction that the Hamiltonian has no sign problem, and you also say, we're going to start with some easy to prepare Hamiltonian, some Hamiltonian where it's easier to prepare the ground state, and we're going to follow an adiabatic path. For simplicity of presentation, we'll not necessarily assume that this path is a linear combination of two things, but I think with some gadgets, you could reduce it to that case. Well, imagine that you follow an adiabatic path of Hamiltonians with no sign problem, starting with something easy to prepare the ground state, keeping the gap from becoming too small. It can only become polynomially small. The path should not be too long. It should be only polynomially long. You have all these different things like the matrix element should only be polynomially big and so on. The Hamiltonian should be polynomially sparse, and ending at some final Hamiltonian. You want to ask, what is the power of this model? Is this model, it's at most BQP, it's at most this MA, so it's somewhere in the intersection. You might wonder, is it just P? Is it just what you can do in a polynomial time classical computer? So the point of this talk is to prevent strong evidence that it's not, that it's more powerful than anything you can do on a classical computer. And the basis for this evidence is showing that what we call relative to an oracle, it can't be simulated efficiently classically. What does this relative to an oracle mean? This is a standard thing in computer science, but I had to learn this coming from a different background, and maybe it's worth saying a few words about it. If you just ask for the problem of, here's two different Hamiltonians, which are some local terms, like this x and h sub z, and maybe x is this Pauli term and h sub z is the sum of zi. Well, this thing is in BQP, and no one has ever proven that BQP is different from P. That would be, a completely earth-shattering result in computer science. Even much weaker things would be earth-shatteringly powerful. So we don't expect to prove that. But what you can often prove is that relative to an oracle, you imagine that there's a black box, and this black box will answer certain questions. In this case, the black box, what it will do is you'll tell it a particular value of this parameter S, and you'll give it a computational basis state. You'll say, starting from this computational basis state, what are the other computational basis states to which we have non-vanishing matrix elements, and what are those matrix elements? And the oracle will answer. And you can keep querying the heroic oracle. You can start with the particular one, query ones that you can reach from that, query ones that you can reach from that, and so on. And this kind of setting is one in which hardness results are proven. And it's a natural one to consider, because if you look at all the kinds of optimization, kinds of algorithms for simulating this problem, they basically call some function that returns the value of the Hamiltonian of particular choices of parameters. So I'm going to prove that relative to an oracle, this can't be simulated classically. I'm only going to very quickly sketch it in the time allowed. So no variant of these programs could do it. Maybe there's something very complicated that uses some structure of the Hamiltonian, but we believe it can't be done. Now, let me say, for me, the motivation is not necessarily the adiabatic algorithm. I think if we ask about the applications to optimization, I think there's, in my opinion, overwhelming evidence that if we just take this h sub z to be some completely unstructured optimization thing, some completely unstructured term, like coming from some max 2 set, then 1 second. I'll be there in a little bit. Okay, I'm talking. Hey, bud, I'm giving my talk. Okay, I'll be back in a minute. And if you have some, if the h sub z is some max 2 sat or whatever, and x is just this transverse field driving term, you should generically expect that the gap is going to be super exponentially small. This algorithm is not going to do well. So if you want to look for cases where the adiabatic algorithm does well, you need some kind of structure in the objective function. And the examples I'm going to construct are going to be some very complicated structure in the particular Hamiltonian. So before, though, that we try to break all classical algorithms, let's try to break the most natural, commonly used classical algorithms. There are other ones. And the most natural, commonly used classical algorithm is path integral Monte Carlo. So the idea of path integral Monte Carlo is that you have, it will often suffice not to compute some properties of the Hamiltonian, but to look at the partition function. So if we have just some fixed Hamiltonian rather than this parameter dependent one, we have some partition function, which is the trace of e to the minus beta h. Beta is the inverse temperature. As beta gets large, this e to the minus beta h will converge to some projector onto the ground states. And if the gap is only polynomially small, beta only needs to be polynomial large to get this to good approximation. You can use a path integral for this. So there's a number of different forms of the path integral, but what you can imagine is that we have some time parameter, imaginary time parameter, tau, that goes from 0 to beta. And we have some configuration of the system. Now, of course, the configuration of the system is really maybe the state of all these spins, if it's made out of n different spins or whatever. But I'll just draw it on a single line for schematic purposes. And what you consider is you consider paths where it stays in some configuration, jumps to some other configuration, stays in that one for a while, jumps, and so on. You look at periodic paths because we're looking at a trace. You can also consider ones with open boundary conditions. And each of these paths comes with some weight. And the weight comes with two different factors. One is when you stay in a state for a while, you get a weight that's e to the minus beta h times the diagonal term for that state. And then when you jump from one state to another, there's a weight that's the matrix element between those two states, proportional to the matrix element between those two states. So the nice thing is that if the Hamiltonian has no sign problem, not only do you sum over paths, but you sum over paths with all the weights are non-negative. So it's just like a classical partition function. You're summing over a bunch of configurations rather than the configuration a single time, it's the trajectory, and they come with some weight. And so you can apply standard algorithms to do sums over to do sums over configurations like a Markov chain Monte Carlo. So you start with one configuration, which will be an entire trajectory. You allow a jump to another configuration, a jump to another configuration. You accept or reject according to some metropolis probabilities. If you're lucky, you might be able to figure out some cluster moves where you allow more complicated moves all at once. And then by doing this, if you don't get stuck, then you can sample the properties you want. But of course, in general, you will get stuck, right? A particular example of a Hamiltonian H would be just a completely diagonal Hamiltonian, a classical one. And then this becomes the same thing as classical Monte Carlo for a classical Hamiltonian. And we know that that gets stuck all the time. So by summing over these things, we know in general you'll get stuck. But the question is, in this particular case, will it be possible to take advantage of the adiabatic path to get rid of this getting stuck problem? So people have tried a very natural algorithm, which is that you start at s equals 0, you equilibrate, you change s a little bit, you equilibrate some more, you change s a little bit, you equilibrate some more. And what you might hope is that there would be some relationship between the equilibration time of the Monte Carlo and the gap of the Hamiltonian. And there's one particular case where there is a nice relationship between them. Imagine that we have a Hamiltonian, and now I'm going to draw again a one-dimensional graph, and this really would be for particle in one dimension. So you have some potential v of x that depends upon some parameter x. That is the worst line I've ever drawn. Sorry, it's hard to draw on this vertical laptop screen. Imagine that the potential is some double well potential. So it has like a single well that's a deep and another one that's there. So initially the ground state is here. Now imagine that we take the well on the left and we imagine slowly changing the height of the well, making it a little deeper, and then a little deeper. Well, as we lower the well on the left, eventually the ground state, instead of being mostly localized in the well on the right, will go to mostly localized in the well on the left. And you can ask two questions. One, how big is the gap, right? I mean, if there's very small tunneling amplitude between the two wells, then right when the heights of the two wells are the same, the splitting between the two lowest energy states will be very small. It'll be proportional to that tunneling amplitude. At the same time, you can also ask, how quickly does it equilibrate? Initially, you're in some configuration where the right trajectories are all in one well, then they're all in the other well. And how quickly can you equilibrate as you sweep it? In this case, it turns out there's a very tight relation. You know, if one of them is polynomially small, then the other is only polynomially small. In this case, the simulation will succeed when the adiabatic algorithm succeeds. But there are other examples. And this is something that Mike Friedman and I looked at a lot, where you can make the gap not become small, but keep the gap of the Hamiltonian large, but you can make the equilibration time get bad. And as an example, imagine now I'm going to change the, so this is really like trying to construct things which will break path integral Monte Carlo by making the gap stay big, but making the equilibration time get long. And one of the problems is that this path integral Monte Carlo looks at trajectories. And so you can imagine a situation, I'm going to imagine a situation where you have the particle can kind of live on a figure 8 or it can live on another site, which I'll denote X. And there's a hopping between the two things. And what I want to imagine is that I start initially on the X. I'm going to tune the energy on this X. I'm going to tune the strength of this dashed line hopping. I'm going to start with the energy on the X very low and the hopping weak, maybe the hopping 0. So initially the particle is always on that X. That's just a single state maybe. Then I start to turn on the tunneling between the X and some specific point on the figure 8, and I raise the energy to the X. Then I slowly turn off the tunneling. And either at the end, the particle will wind up on the figure 8 or it will end up on the X. And the thing that will determine it is whether the ground state energy on the figure 8 is above or below the ground state energy of the X. That there are some questions about, like, can we keep the amplitudes large enough between these and so on to keep the gaps not too small. But if we do it slowly, that's what will happen. Now, path integral Monte Carlo has a problem. If you look at the trajectories you should be sampling, they should jump onto this figure 8, make some loops around the figure 8 and go off. So in general, a trajectory might jump onto the figure 8, go around and then jump back off, or go around the top loop and then the bottom loop and so on. And you can describe these trajectories by some words. I'll write an A if you go around the top loop and a B if you go around the bottom. And in general, a trajectory might be some kind of complicated combination like A, B, A inverse, B to the minus 2, and so on. Describe me. Go around the top loop, around the bottom, back around the first, 2 times, or back around the second, and so on. There are words in a free group, the fundamental group of this particular thing I've drawn. But path integral Monte Carlo gets stuck in one trajectory. It can only stay in one particular trajectory. And there's a, in one particular topological sector, sorry. It can go around the top loop, but then it has to come back off the top loop, or else it's not a well-behaved trajectory that it's sampling. And in this particular case, if you look at a word on the free group of length proportional to the inverse temperature proportional to beta, the number of them is exponential in beta. So path integral Monte Carlo will misestimate the weight of the trajectories on the figure 8 by an amount that's exponential in beta. That means it will misestimate the energy on the figure 8 by an amount of order 1. So it makes a large error in the energy, and in the end, it winds up incorrectly deciding where the particle should go. Now, this, of course, is a specific algorithm. The goal is, from a theory point, well, from a computer science point of view, maybe it's interesting to ask, can we beat all algorithms? Can we come up with something where no algorithm will succeed? There have been other algorithms, for example, diffusion Monte Carlo, and there was work by Jordan and collaborators on that, and they showed that you can make that one fail by looking at obstructions having to do with L1 versus L2 norm. Open world line Monte Carlo, Mike Freeman and I studied that. That involves combining this topological obstructions with some use of L1 versus L2 norm, and so on. So the question is to come up with something that makes every algorithm fail. And this is what now we know you can do within this Oracle model. And the key is to use this topological obstruction. And first, there's a certain, I'm going to just only have time to very, very quickly sketch the construction. The idea is first to make a certain reduction. So this construction is going to have some graph. What I mean is we're going to think about a discrete space of states where there's going to be some graph of possible configurations, some hopping between them with certain amplitudes. And I'm going to also think about having this X somewhere. And I'm going to think about particular cases where I just change the energy of this X and change the tunneling on and off this graph. And what I'm going to look for is I'm going to look for 2 different graphs, which have the property that their ground state's energy differ by a good amount, by a decent amount as quantum Hamiltonian. So that in one case, depending upon how I tune the energy of this X, you should wind up on one side. In the other case, you should wind up on the graph. In one case, you should end up on the X. These graphs represent possible states, and the edges represent non-vanishing matrix elements between them. And I want to arrange it so that the amplitude of the ground state on this graph has a reasonable amplitude on this state that the dashed line connects to. That's otherwise the tunneling between will be small. And this is kind of a cartoon of the adiabatic algorithm. It's just carrying really the essential features of it, that like the inverse polynomial gap carries into this inverse polynomial amplitude to tunnel on and off. And it's just looking for graphs with certain properties that are hard to distinguish classically, but quantumly have rather different energies. Even though the ground states still have amplitude on a certain site, but they're very hard to distinguish classically, even though quantumly the energy is different. Now, there's some more steps in order to proving that this means you can't solve the optimization problem. Because in this particular case, you just say, oh, I'll just try the 2 possibilities. Either you're on the graph or not. I just run, I just force one of the two to happen and try them both. So there's some other steps to making it so that if you can't solve this problem, then you can't solve what the adiabatic algorithm can solve. So we look for two graphs which are hard to distinguish. Now, another step is when I talked about the path integral Monte Carlo, I was saying that it has trouble with topological sectors. So imagine some path that on this graph that starts, at this site here. Oops, I didn't mean to do that. I hit the wrong thing. Sorry. Starts here and then hops onto this site, hops onto that site, and hops back to where it starts. In this case, the algorithm can see, a classical algorithm can see, oh yeah, I returned to where I started. And so it can start to figure things out. I want to make it impossible for a classical algorithm to know that it's returned to where it started. I want to make it so that when it moves on a graph, it's blind. Essentially, all it can see is how many neighbors do I have? And it can query a neighbor and ask, how many neighbors does that have? But it never knows when it got back to where it started, unless it gets back to that one particular vertex, which couples to the X. And the way we do it is we take this graph and we sort of blow it up. We take each of these small dots and we replace it with a large number of little dots. Same thing here, exponentially many. And we replace each of these edges between them. So there's an edge between these two small red vertices with edges between all the dots in them, but in some totally random way with some random permutation applied when you go from one to the other. So you're hopping along, and as you hop from one edge to another, you just go from one of the dots here, one of the little vertices, to a completely permuted one over there, to a permuted one over there, and a permuted one over there. When you follow a loop on your original graph, the odds are when you go to these little vertices, you won't return to where you start, and so you won't recognize it. So you make it so that your classical algorithm is essentially blind to all information about the graph, except as it walks, what are the number of neighbors. And at this point, we reduce the problem to building two graphs where if all you can do is do this walk blindly and ask about the number of neighbors, where classically you can't tell the difference, but quantumly there is a large difference. And such a construction exists. The construction is based on starting with a particular graph, which is, what is this graph? You take a line, a short line of some length. So I'll just draw it as, say, 5 long here. And I have 5 long and 4 high. And what you do is everybody couples to everybody in the neighboring edge. So like that goes to that, to that, to that, that goes to that, to that, to that, to that, and so on here. So it's a particular graph which you can move around on. And then you start somewhere in the middle, and I either connect the left edge to the right edge or not. The two different ones, and connect means everyone on the right edge goes to everyone on the left edge. I connect them or not. And that change causes a difference in the energy. Now it'd be easy to tell the difference, you just having those connection or not. You just start somewhere in the middle, do a random walk, and eventually either you hit one of these vertices on the edge, in which case you have fewer neighbors because it only has neighbors back to the inside there rather than to the other side, or you don't. So this is an easy one to solve. You just do a random walk and you hit the boundary or not. But then what I do is I take the graph and I decorate it. On every single vertex, I attach a tree, which goes for some depth, like that. And then the tree, sorry, it's automatically correcting some of it to triangles, but you just attach a tree off every vertex. So now when you random walk, you tend to get lost on the tree. So you start, you walk, you walk, you walk, you get, by chance, you take a step onto the tree, but you can't tell the difference. When you're on the graph, it's very different from the tree because there's all these self loops, but the classical algorithm can't tell that. You take a walk on the tree, eventually at the end of the tree, maybe you realize, oh, I shouldn't have taken a walk on there. I better go back to where I start. That slows the classical algorithm down a lot because it keeps taking all these false steps on the tree. But it can still do it in polynomial time. But then you decorate the tree with more trees and more trees and more trees and more trees. And you make this situation where the quantum algorithm, what the quantum wave function does, the quantum wave function stays concentrated in what I've drawn in black because there's all these self loops. And as a result, the L2 norm of the wave function is quite big there. But the L1 of the norm of the wave function is quite big on these other trees coming off. And the classical algorithm, since all it can do, anything can do when it queries the oracle is just get neighbors and pick them. And there's no way for it to avoid by chance following these trees. There's a lot of steps to proving that there's no way to do it, but no classical algorithm can do it. And one can then show that there's a lower bound of n to the log n on the time for any classical algorithm to solve this. Time, I should say, number of queries to the oracle. This allows the classical algorithm to do any kind of computation it wants. It's bound based on the number of queries to this oracle. So let me just close in the 2 minutes that remain. 2 interesting questions. One is, this is barely super polynomial. It's n to the log n. It's not 2 to the n. It's not polynomial, but it's barely super polynomial. So you can wonder, can it be improved to something that's 2 to the square root n, or maybe 2 to the n? Can you really prove a real slowdown for something that's not this quasi polynomial time? You prove something that might be an exponential slowdown for the classical algorithm. Or conversely, can you prove that one of the known, or perhaps some new classical algorithm, always is able to do it faster than exponential? naive worst case algorithm is still exponentially slow. Can we prove something faster classically? And then the other one is, just to a very optimistic and broad thinking way to say it. There was Shor's algorithm, of course, which had an enormous impact on the field of quantum computation, cannot be understated. But there's also Simon's algorithm, and Simon's algorithm is an algorithm there you provably have a I think exponential speed up of quantum over classical, but it's exponential relative to an oracle. Now, if you take that particular oracle in Simon's algorithm and instantiate it in a particular way, you get Shor's algorithm. There's not a proven speed up in Shor's algorithm, but we know no classical algorithm that matches it. So here we have a particular oracle, and relative to this oracle, which answers very strange questions about graphs, we can prove that this quantum algorithm has a speed up. Now, can we come up with an instantiation that will be some actually useful case where there's some useful quantum algorithm? I don't know. I would be a great question if anyone could have some useful thoughts on that. So let me stop here and take questions.
Okay, thank you very much. So we ask participants to write your questions in the Q&A tab, if you have any, or the panelists or speakers can ask questions directly by turning on the microphone. If you have questions, we have several minutes.
I have a question, Daniel here.
Please.
So this last comment, Matt, was very interesting about getting rid of the oracle. What can you speculate on what this algorithm would actually solve in that case? What would be the computational problem?
Yeah, I don't know. I mean, I don't have any completely useful idea. I've had some vague thoughts that one thing might be something to do with groups, because you can construct certain representations of groups and describe the representation of groups in terms of certain generators of the group and relations on the group, and that winds up corresponding to certain configurations in terms of circles and things capping off the circle and so on with disks. And so I've had some thought that some kind of way of analyzing some particular group, I don't know where it would arise. I mean, of course, groups arise everywhere. I mean, even like a lot of problems in number theory have to relate with groups. Might be a particular kind of instantiation. I mean, obviously, distinguishing a free group from some other group. I mean, I'm just guessing here. I don't have any more coherent thoughts than that.
Thanks.
Okay. Any other questions?
I mean, in a sense, I guess I could say that, the way in the construction I do, the way that I reduce this question of like really finding the optimum to this question of being able to decide whether the energy is bigger than or lower than something is a rather like ad hoc way in which, because this quantum algorithm is just able to learn one bit a little better than a classical algorithm. It can learn whether you're in this graph or whether the graph's energy is bigger than or less than this better than the classical one can. That's only learning one bit. So I had some ad hoc way in which you then learn n of these by repeating it n times and then use that essentially as a dictionary key into something else. That's all sort of very ad hoc. So even if there were a more practical instantiation of this question of whether an energy is bigger than or less than something, might be useful.
Okay. It seems that Elizabeth Crossan has turned on the microphone. Do you want to ask a question? Please.
So maybe it's not super important, but have you thought about the equilibration time of quantum Monte Carlo for these instances? Is it quasi-polynomial or maybe worse than that?
Oh yeah, no, that's a great question. I mean, whether like these particular, because whether these particular instances would be exponentially long or not. I'm not sure. Yeah, it might be rather slow in this, or even to tell you the truth, I don't know. Some of the proof that it takes n to the log n time, because it's a little hard to prove that no classical algorithm can do something. So some of the proof was done by giving the classical algorithm extra information, which can only speed it up, and then showing that, well, given this extra information, the classical algorithm will always choose to do this because it knows there's no point in doing that. So some of it, I still don't even actually know a classical algorithm that always solves this one n to the log n. So yeah, it's maybe that one does. I don't know. It's a great question.
And maybe another one, if you allowed yourself to use any quantum algorithm, could, would that, is there a quantum algorithm that would be even better for this task than the adiabatic algorithm without a sign problem?
It's a good question. I mean, it's quite possible that on this particular graph that a standard quantum walk would solve it pretty quickly, because these loops are, I think of the loops in this context as being so that the ground state amplitude gets increased on these, the L2 norm of the ground state amplitude gets increased on this graph at the middle. And that's really because, like, when you think about the trajectories, you sort of like have multiple ways of going to the same point. But I would guess that a quantum walk would probably have some kind of constructive interference, and so would also solve it rather quickly.
Thanks.
Okay, the time is almost up. So thank you, Matt Hastings. So let's go on to the next talk. Therefore, consecutive talks by 4 people, and you can ask questions at the end of this set of 4 talks. So the first speaker is Panataraya. Please go ahead.
Hello, everybody. I will talk about combined continuous error suppression and error correction for quantum annealing. So the problem is one logical qubit, which is encoded into 3 physical qubits using the bit flip code. The physical qubits are subject to thermal noise, and they are described by this Hamiltonian. The first part of the Hamiltonian describes the logical state evolution, and the second part describes the error suppression following the Jordan-Farey-Shorter scheme. These terms are just a linear combination of the stabilizers of the code Z12, Z23. And this parameter eta p is the energy penalty, which is essentially the energy gap between the code space and the error subspaces. The goal here is to preserve the ground state population by error suppression and continuous correction of errors. In this 3-qubit system, we have 8 levels. The lowest one is the ground state. And initially, we start in the ground state, and we would like that the system state remains there. However, because of coupling to the environment, there are thermal excitations that bring the state from the ground state to one of the excited state in the error subspaces. And the idea here is that when you continuously monitor the error syndromes, then you detect where the system state is in which of the error subspaces, and then you when you detect the error, then you apply the error correction operations here x1 or x1 x3 or x3 in order to move the state back from the excited state back to the ground state. In order to know which error correction operation you need to apply, you need to monitor the stabilizers, and we do the continuous approach, where the measurement output signals here, this IZ12, for example, is it has the signal part, which is this trace term, and then you have the noise. The trace term is just plus or minus 1, but the noise has a strength much larger compared to 1. So because of this strong noise in these continuous measurements, what we need to do is to first do a time averaging of the raw measurement signals in order to obtain the time average error syndrome signals that are further processed. The time integration that we use here is this parameter tau, which is optimized. We have a double thresholding error detection protocol where uses 2 error thresholds, this θ1, θ2. And there are some conditions that if these integrated error syndrome signals R1, 2, or R2, 3 is satisfied, then you say my state is in the code space or in one of the error subspaces. And based on this information, you apply certain discrete error correction operation. Now the results, on the y-axis, you see the instantaneous ground state infidelity, on horizontal axis time. The red line is what you obtained when you use only the Jordan-Farey-Shorter scheme with only error suppression. And in the blue line is when we combined with continuous error correction. Here you see that the final ground state infidelity is reduced by a factor of 20 here. When we zoom in the blue line, we see that there is a rapid increase of the instantaneous ground state infidelity. And then we realize that this initial increase is because of undetected errors that happen near the end of the annealing. So this initial increase can be eliminated by using a postulation procedure at the end of the process. So this is the main result when we combined error suppression with continuous error correction in postulation step at the end of the operation. We have a nearly 2 orders of magnitude improvement in the instantaneous ground state infidelity compared to the original Jordan-Free short scheme. Yes, that's all. Thank you.
Thank you very much. So we are just on time. So let's move on to the next speaker, Dr. Yuki Bando. So please go ahead.
So, hello everyone. In this talk, I briefly talk about the experiment with the Q-Track mechanism on a quantum annulars DWave 2000Q. Firstly, I should explain how quantum annular work. Quantum annulars like DWave 2000Q dynamically control the balance between the quantum fluctuation term and the target Hamiltonian describe optimization program while following the annealing schedule in this figure. Here, annealing schedule is a function of dimensionless time S, which is manually characterized by annealing time scale TA. So as you know from the Adiabatic Theorem, if annealing time scale TA is sufficiently large, we can obtain correct solution of the target to Hamiltonian through quantum annealing process. In this study, however, we focus on the phenomenon near the phase transition point related to the annealing time scale TA, which is called the Kibbles-Leck mechanism. So as I said in the previous slide, the annealing time scale TA is closely related to not only the performance of the quantum annular, but also the physical phenomenon called the Kibbles-Leck mechanism. The Kibbles-Leck mechanism describes the scenario of the formation of the topological domain during the dynamical control of the system. So we shortly explain this mechanism on quantum annulars. First, while proceeding quantum annealing with finite annealing time scale TA, the relaxation time of the system increases as the system approaches the phase transition point. Next, at a certain point, the relaxation time exceeds the remainder time to phase transition point, for example, this point. So finally, under this situation, since the state cannot follow the change of the system Hamiltonian anymore, the system flares out with several separated topological domains accompanied with boundary. We call these boundaries defect or kinks. Here, the theory of the Kibbles-Leck mechanism provides a scaling law of this defect density with respect to the annealing time scale TA. So our object is to consider how this scaling law works in real quantum annealing device. So we would like to show our several results by using one-dimensional Ising model as a target to Hamiltonian. So this figure shows the log-log plot of the defect density versus annealing time scale TA on two different quantum annulars, DWave 2000Q at NASA and at Barnaby. So this figure shows our result shows scaling exponent on these real quantum annulars distribute from about 0.20 from this 0.20 to 0.34. So these observed exponent are closer to the theoretical exponent 0.28 of an open systems coupled to boson field than 0.5 of isolated systems. So thus we conclude the current quantum annulars follow the open system Kibbles-Leck mechanism rather than the ideal isolated one. We obtain more results about the defect distributions. In isolated systems, it has been found that from the previous studies that the defect distribution becomes Gaussian and all cumulant are proportional to the first order cumulant being the average of defect. So we revealed that this isolated system's defect distribution theory can hold even in the case of open system. The observed defect distribution are Gaussian at almost all annealing time scale TA, as shown in this left figure. So in addition, the variance and the third moment around the defect average are also well proportional to the defect average, as shown in this right figure. So to our knowledge, this is the first case quantum annealers provide new physical insight to us. That's all. Thank you for your attention.
Okay, thank you very much. Okay, let's move on to the next speaker, Dr. Mustafa Kazri. Can you go on?
Yes, let me share my screen. All right, can you guys see my screen?
Yes.
Okay, great. So hello everyone, I'm Mustafa Kazri. I work at USC with Daniel Leader on the QEO QAFS project. And today I wanted to talk to you about capacitively shunted flux qubits and how we extract circuit parameters for these flux qubits in our system and how we validate our circuit models that we use for these systems and design different annealing paths. So essentially the CSFQ you can see on the right, for us, it's just two large junctions forming Z loop and smaller junctions forming X loop with their own biases that you can use to control the parameters of a tilted double wall potential. We have persistent current readout on our qubits, and they're also coupled to a dispersive readout resonator. Essentially, just looking at the Hamiltonian model that we write for this CSFQ circuit, we can see that you can see how the different X and Z biases enter into the model. And let me just also mention that we can see that how asymmetry of the junctions can essentially rescale the persistent current and induce some extra Z bias into the qubits. Which essentially what it does is that it looks like some form of a nonlinear crosstalk. You can see it just changes the degeneracy points of the point of the qubit, but it's fine because we can use this exact thing that changes the degeneracy of the qubit. We can just use it to experimentally extract this symmetry parameter by just performing dispersive measurements on the qubit. And we need this because this is good for us to understand our circuit parameters, but it is also good for us because we can use it to essentially choose annealing path that corrects for this asymmetry, essentially canceling that nonlinear crosstalk, which here we're showing that then you would have to go along this curved path in the XZ plane of the fluxes, and then you can get some nice single qubit experiments we demonstrate with that, reducing the S-curve width. But another interesting thing is to let's look at the circuit itself, specifically its higher levels. And here you can see that we can essentially fit our experimental spectroscopy data of the qubit to the circuit model that we have, and we can extract some parameters for the circuit. So let's keep this fitted model in mind because we're going to use them later. We can essentially try to play with these annealing paths a little bit. For example, we can use these black line annealing paths to intentionally close the qubit gap as we're annealing the qubit, and just perform a persistent current readout measurement at the end. And then you can see we end up with this strange looking plot with these peaks and features and everything. But we can actually use this plot to investigate the multi-level structure of our circuit and validate our circuit model. For example, let me tell you what happens. For example, at this dashed line, at this peak, what is essentially happening is that at this location, as we're annealing our qubit, we close the gap and start a series of cascaded level crossing that just keeps transferring the qubit population into higher states. And as new levels come into play, we end up with qubit populating different eigenstates, and we get these different peak features. So just by this, we can use the previously fitted model that I showed you guys, and just extract where we expect the location of these peaks would be, which we're showing with these orange circles, which you can see just using those independently measured circuit parameters, using the asymmetry measurement and the spectroscopy. We can just predict these features which are due to the higher eigenstates of the circuit. And we could also more or less confirm this model by just performing some adiabatic master equation simulations, which essentially you can see it's this dashed blue lines, which qualitatively captures all the behavior of these peaks. It's missing the width of the peaks because we're just not using, we're using high frequency noise, which we know is not true for most superconducting circuits. And then also we're looking at the eigenstate populations of the circuit. We can see that exactly at the locations of those peaks where we were expecting population transfer to higher states, you're observing those population transfers to higher eigenstates of the system. So in summary, we just have this QFQ model that we can use to analyze annealing paths, correct for them, for example, in case of asymmetry in a linear crosstalk, or investigate the higher level of structures of our circuit model and validate it. Thank you very much.
Thank you, Mustafa. So let's move on to the last talk of this session for short talks. The next speaker is Dr. Zhenya Mozgunov. Please start.
Hello. So I'm Zhenya Mozgunov, and today I'm gonna talk about an adiabatic theorem, extension of adiabatic theorem for unbounded Hamiltonians, and also application of the adiabatic theorem for superconducting circuits. So the statement of the adiabatic theorem concerns a time-dependent Hamiltonian and evolution rate.
Can you share the screen? The screen is...
Really? Oh.
It is not on.
Sharing is paused. Bring your shared window to the front. Sorry, what? Okay. Is this what I'm doing? Sorry. So can I try again and just share desktop and then view full screen? Okay, does this work?
Yeah, okay.
Sorry about that. Okay, so again, this is just my first slide, and I'm talking about the adiabatic theorem, which I assume that you've seen it, it's 100 years old. And the idea here is that it's about the leakage from the subspace separated by a gap as it evolves by a sometimes dependent Hamiltonian. And that leakage is bounded by 1 over t. Big O notation is usually used when people present the adiabatic theorem. Just by definition, the big O notation actually means that there exists some constant theta that stands in this inequality. And the entire talk is about this constant theta and its dependence on the parameters of the Hamiltonian and the gap that separates the subspace from the rest. Now, so we actually present an explicit expression for this constant. In the literature, there was previously an explicit expression for this constant in the paper by Jansen, Ruskaya, and Saylor. And the problem with that expression was that if the Hamiltonian has an unbounded derivative, like for example, any time-dependent harmonic oscillator Hamiltonian would have that, then their constant is infinite. However, actually it is possible to generalize the bound so that the constant is finite, which is what we do. Another interesting observation is that their constant is proportional to the dimension, but it doesn't have to be. And the third thing that we do is that neither of the formulas were ever actually used in practice to the best of my knowledge. So we do the computation brute force and compute it with all the prefactors. And I will explain what these notations mean. Now, the unboundedness, of course, appeared in the literature about the Adiabatic theorem before, and the best that was done is that people noted that an additional assumption is needed for unbounded Hamiltonians for the Adiabatic theorem to be true. In this paper, this assumption is stated, but no explicit dependence on the quantity appearing in the assumption has been presented. We use a different assumption, which is, in my subjective opinion, easier to work with, and we present an explicit dependence on the quantities appearing in this assumption. Now, the dimension thing was actually really easy, so the Janssen Ruskay-Seller could have easily written it down. It's just that that wasn't their goal. But if our goal is to work with large, low-energy subspaces, like, for example, in DWave, we have a circuit model, which is sketched in the corner. And then we have a qubit model, which is 2 to the n dimensional, where a circuit model is infinite dimensional. And we wanted an adiabatic theorem for staying in the qubit subspace first, before we even talk about quantum annealing. So in that case, this simple idea allows you to get rid of 2 to the n factors in the adiabatic timescale. Now, we also wanted, as I said, a simple example. And in the previous talk, Mustafa presented the CSFQ. And this is a extremely simplified CSFQ Hamiltonian, where the control fluxes are chosen in such a way, as experimentalists normally do, to implement a quantum annealing of this single qubit. Note that you cannot implement it perfectly. There is always some non-zero tunneling in the end of the anneal, because the barrier cannot be infinite in practical circuit Hamiltonian. Also, experimentalists call the gap to the non-qubit states plasma frequency. Now, our result, as I said before, is this, which contains a intuitive ratio of the qubit frequency to plasma frequency, but also contains this 1 over delta that I haven't heard anyone discuss before. So it turns out that being precise in our quantum annealing schedule is actually bad for the adiabatic timescale. Now, for this particular example, which is a bounded Hamiltonian, there's no difference much between JRS and our new bound. There's just a logarithmic factor. But of course, if you try to apply it to DWave Hamiltonian, then the theta JRS would be infinite, and our new one will still be roughly of the same value. So that is my talk. Thank you.
Thank you very much. So 4 consecutive talks have been finished. And can you stop sharing the screen? OK. So participants can ask questions by typing in your question in the Q&A tab, or speakers can ask questions directly by turning on the microphone, if any. We have 5 or 5+ minutes for that purpose. May I myself ask question to Dr. Atalaya? Your result of error suppression seemed very impressive, and I understood that you didn't use a particular structure of the problem. How generic is the scheme?
Sorry, what is the numerical scheme? Or
No. The
sorry.
scheme of error suppression.
Yes.
Can you similar results for any other problems?
No, we have so far we have considered only the case of the bit flip code, and where the error suppression terms are just the stabilizers of the code.
But you don't mean that you use the specific structure of the specific problem for error suppression in a formulation?
Yeah, well, we consider the thermal errors. So the coupling between the system operators in the bath are just the bit flip operators, X1, for example, and this linear coupling to the bath of oscillators.
Yeah. So that's generic, I understand. Okay. Any other questions for one of the speakers, any of the speakers from the audience or the panelist speakers. Okay. If not, we may be able to go ahead to the next longer talk. You may have a few extra minutes for that. Please go ahead, Professor Crossan, Elizabeth.
Thank you. Yeah, thank you all for attending, and to the organizers for the opportunity to present this work. Okay, so quantum annealing and the sign problem. So, the role of the sign problem in quantum annealing has been, I would say, a major guiding question in our field in the past decade, stochastic versus non-stochastic Hamiltonians. And there's been some big developments this year, and I would say that this year is a turning point in our understanding. So two of the main questions to consider are, when do we know for certain that classical algorithms can efficiently simulate stochastic quantum annealing? And maybe the more interesting question, so will non-stochastic Hamiltonians enable that elusive scaling advantage specifically for optimization with quantum annealing? So on the topic of stochastic simulation, the main result of the year is this new Oracle separation that Matt Hastings just presented. I also want to briefly mention some work that I did with my student on high temperature simulation results. But most of my talk will focus on the second question about non-stochastic advantage. And so here in this paper, we define a new designing map that from non-stochastic Hamiltonians to stochastic Hamiltonians. And this allows us to compare them somewhat directly in the setting of adiabatic optimization. And the conclusion is that the designed stochastic Hamiltonians tend to have larger spectral gaps. And so we are calling into question the prospects for a non-stochastic advantage in optimization. Now, I'll qualify that carefully as we go on. But first, just talking about the status of stochastic simulation. So, Hastings' proof of this Oracle separation, a superpolynomial Oracle speedup, resolves a problem in Hamiltonian complexity that has been open for at least 15 years. So that is, I would say, one of the highlight results of the year across all parts of quantum information. Okay, so going in the other direction, so can we prove new simulations for stochastic QA? So this result that we had earlier this year says that path integral quantum Monte Carlo converges efficiently for generalized transverse Ising models, the kind we usually consider, at temperatures above 2 times the interaction degree plus 2 in units of the coupling. So you can actually insert, h bar in Boltzmann's constant and turn this into a practical sounding result. That is, if you have your interaction degree of 6 with couplings of 1 gigahertz, this temperature above which we guarantee efficiency of quantum Monte Carlo would be 800 millikelvin. Now, obviously that's much warmer than current superconducting devices. So no one is proposing to get a quantum advantage at those temperatures. We're off by maybe a factor of 10 or more. But I think one of the main things I want to say about this result, so we now have 3 general conditions that imply rigorous quantum Monte Carlo simulations of transverse Ising Gibbs states. These are 1D transverse Ising systems at any constant temperature, ferromagnetic systems, even down to inverse polynomially small temperature, and then this recent result of high temperature systems. And so what's notable about these 3 cases are these are the same 3 cases for which we know efficient simulations of Gibbs states of classical Ising models, because these are the cases that avoid NP hardness. So the stochastic simulation story between these three results and also the oracle separation of Hastings may be complete in terms of natural questions that we have a reasonable hope to answer with the theoretical tools we have. But we've known in this community, we've had practical evidence for many years that quantum Monte Carlo is efficient. So this is just the rigorous results catching up to what we've seen in benchmarking. So the real question is, what can we do with non-stochastic Hamiltonians? Just reminding ourselves of the history, we started to turn attention to non-stochastic Hamiltonians as it became increasingly unlikely to find a scaling advantage with transverse field annealing. So the main arguments for turning to stochastic Hamiltonians have been, non-stochastic Hamiltonians have been indirect. So adiabatic computing with non-stochastic Hamiltonians can be universal for quantum computing, but it'll be relevant for this talk that the final Hamiltonian in these universality constructions is much more complicated than a classical optimization Hamiltonian. Okay, another argument for non-stochastic Hamiltonians is that we've known for 40 years, 50 years, that practically efficient quantum Monte Carlo simulations break down in the non-stochastic case because of the sign problem. Okay. But neither of these arguments directly implies that we'll see an advantage in non-stochastic QA for optimization. So the message today is, well, we'll introduce this designing mapping, and it allows every non-stochastic Hamiltonian to be compared with a stochastic counterpart. And we find the stochastic counterparts almost always have larger gaps. But it is a probabilistic statement. So it does not contradict important existing results like the exponential improvement by non-stochastic interactions in the Pspin model. Our results really just imply that inserting random non-stochastic terms is unlikely to provide an advantage. So here is the definition of the designing operation. It simply just forces all the off-diagonal matrix elements to have the same phase, the phase they would have if the Hamiltonian were stochastic. So here is your original Hamiltonian written out in terms of its computational basis matrix elements. And here's the designed Hamiltonian, H bar, where we've just left the diagonal elements unchanged, but we've forced all the off-diagonal elements to be real and non-positive. So right away, this designing is a nonlinear map. It changes all of the eigenvalues and eigenvectors in general. But the key point is that it leaves classical Hamiltonians unchanged, this diagonal part. And so it preserves the endpoints of an annealing path. The designed Hamiltonian can therefore be regarded as a new path through the space of Hamiltonians that connects the same endpoints, the same classical Hamiltonian endpoints as the original Hamiltonian path. And this property of preserving the endpoints is crucial. So designing would not make much sense to consider in universal AQC, where the final Hamiltonian wouldn't be preserved. Or say you were doing adiabatic quantum simulation and you were trying to prepare the ground state of a final Hamiltonian that is itself non-stochastic. Well, then it wouldn't make sense to consider this mapping. It's really specialized to this optimization setting. And then the other thing to mention is that this designing always preserves the sparsity of the Hamiltonian in the computational basis, right? You only have non-zero entries in H bar where there were non-zero entries in H. So it compares the non-stochastic interactions to what are effectively multi-spin stochastic interactions. So we're not just comparing non-stochastic to the plane transverse field, but we're comparing, if you like, plus XX to minus XX. Okay, so because this designing operation is highly nonlinear, we were not able to rigorously analyze it in all generality. So our message that designing increases the spectral gap is based on a variety of suggestive evidence. First I'll describe a relatively quick rigorous proof in the setting of random matrix ensembles, Wigner matrices. So our paper just contains a collection of results. We also show that in certain special cases, for example, let's say your Hamiltonian is written purely in terms of Pauli X operators, and you design the matrix elements in the computational basis. Well, this always increases the spectral gap. So we have some kind of complicated results that relate to the geometry of the ground state probability distribution. And one way to sort of efficiently summarize these results that I won't go into is that if the ground state probability distribution does not change much under designing, so of course the non-stochastic Hamiltonian has non-trivial phases in the ground state, but when you square it, you get a distribution. Right, and if the original Hamiltonian and the designed Hamiltonian have similar ground state probability distributions in the basis where you designed, then on geometric grounds, designing cannot shrink the gap by much. So we don't necessarily show it increases the gap in this setting, but that if these are close, and this assumption of closeness kind of helps deal with the nonlinearity. But maybe the most convincing thing for many of us is a very clear trend in numerical simulations that already emerges at low qubit number. And so all of our analytic arguments support the main conclusion, but what we would really like to address, I would say, are random local Hamiltonians or local Hamiltonians with random non-stochastic catalysts. But these are the most difficult to analyze. So there we rely a bit on a numerical trend, but we can't actually prove the result that the numerics indicate. So there is an open problem here. Okay, so as a first kind of warm-up result, an initial observation is that designing always decreases the ground energy. And the proof of this is just variational. So you start with your original Hamiltonian and your original ground state. Then your proposed, your variational ansatz for the new state, the designed Hamiltonian's ground state is just the absolute value of what you had before. And here this inequality is the variational theorem or variational method, and this you just show by algebra. So this feature, which always happens, the decrease in the ground energy upon designing, this is in some ways, I think the main reason why the gap gets bigger is that the rest of the eigenvalues, they do all kinds of things, but you consistently have the ground state energy dropping, and that tends to create a bigger spectral gap. So as we know, stochastic Hamiltonians are special in their ground states particularly. And so just from this observation, so if the Hamiltonian is positive semi-definite, and we don't change the diagonal elements, well, then the trace of the original Hamiltonian and the designed one are equal. So if you think about it, we have a sum of the eigenvalues. They're all non-negative. They have to add up to some value. We've decreased the smallest one when we design. So this has to increase the spacing somewhere in the spectrum. And if we could just show that the first excited energy of the designed Hamiltonian for some reason got bigger, well, we would be done. But this just isn't true in general. In fact, what tends to happen is that the designed first excited state also goes down a bit, but not as much as the ground state. And that's the reason you get a bigger gap. Okay, so what can we prove? So let's consider an ensemble of n by n random symmetric matrices, let's say with IID entries of mean 0 and variance 1. So Wigner famously showed that the distribution of eigenvalues of these matrices is a semicircle distribution between plus and minus root n in this normalization I'm choosing. And this fact also holds for entries chosen uniformly, say, which we'll use. So it really just depends on the first few moments of the distribution of the IID entries. And since there are n of these eigenvalues, the typical spacing between them is 1 over square root n, because it's root n to root n. And then, you know, a lot is known about the probability that these spacings differ by very much. And also, you know, there's a whole theory of what's happening at the extreme eigenvalue. So we're about to think of stochastic Hamiltonians and ground states in terms of Hamiltonians with non-negative matrix entries and their top eigenvector. So kind of as playing the role of the stochastic Hamiltonians as a random matrix ensemble. So consider an ensemble of symmetric matrices with non-negative IID entries, say chosen uniformly from the interval 0 to 1. And this should be mathematically equivalent. These matrices with non-negative entries and their largest eigenvector are just directly related to a stochastic Hamiltonian and its ground state. Just a shift in rescaling. So basically the point is that each matrix in this new ensemble of non-negative matrices can be obtained from a matrix in the previous ensemble by adding a matrix that has a 1 in every entry. And so this matrix that we're adding has a single huge eigenvalue of n, and all of its other eigenvalues are 0. It's a rank 1 matrix. And so you can just show using some basic tools like Weil's inequality on the eigenvalues and some variational method that what happens is the largest eigenvalue just becomes an outlier. So you've increased the gap tremendously by designing. And so maybe it's not so meaningful or just in terms of the normalization, but basically, you know, you get an arbitrarily large separation between the standard Wigner ensemble, which is related to the GOE ensemble, and this non-negative ensemble. Okay, so if that didn't convince you, here's what the numerics look like for random dense matrices with IID entries. So we define this notion, which is the fraction of non-stochastic winds, so n is the dimension of the matrix. So these are dense matrices. Basically what you see is that the fraction of non-stochastic winds, which are cases where the original Hamiltonian has a larger gap than its designed counterpart, that these go to 0 rapidly with the dimension of the matrix. So this is just saying that, you know, all but this 10 to the minus 6 fraction of these guys have a larger spectral gap when you design them. So it's just confirming what we could prove mathematically. And then the designed case actually just is worse. Sorry, the complex valued case is just worse than the real valued non-stochastic case numerically. Okay, here's some more numerics on these results. So yeah, so we considered max cut problems on 3 regular graphs. You know, there's a lot of different studies you could do on this, but we settled on these, and we considered several different cases. So we considered these alpha ij coefficients on the non-stochastic path change could either be randomly plus or minus 1. They could be uniformly random in the interval -1 to 1, and then the Hamiltonian is fixed as max cut, you know, taken from some graph. And then, you know, if you're really kind of an expert in this, here's another sort of case breakdown we consider. So the Hamiltonian that we've written here has a global bit flip symmetry, and the time evolution in the pure unitary case is constrained to the +1 subspace of this symmetry. And so Tamim Albash had a paper where he explained the non-stochastic advantage in the Pspin model, or related it to a condition on whether or not the ground state energy is in this +1 subspace or not. So the two things that could happen, right? You're sort of trapped in this +1 subspace, and the question is the true ground state energy at the point of the minimum gap, is it outside this +1 subspace? And this seemed to somehow be related to non-stochastic examples examples of non-stochastic enhancement that Tamim looked at. So here's a bunch of numerical data. So let's first focus on this upper square where we're looking at exactly the designing proposal I told you about, and we're just looking at the minimum gap along the anneal, and we're using that to determine the fraction of non-stochastic winds. And what you can see is that you know, the fraction of non-stochastic winds is never that high, right? Already we're pretty far down on this axis. So here you can look at the different curves for whether the coefficients of the path change are chosen uniformly at random or in plus or minus 1. And then also these conditions of whether the true ground state energy subspace. So apparently your best chance of a non-stochastic wind is to take the coefficients uniformly and actually have that condition apply. But it's not so different from not having the condition apply. Now in these other boxes, so this box down here, there's another proposal for taking your non-stochastic Hamiltonian to a stochastic one. The other proposal is to just add matrix elements. So instead of taking the absolute value, you just add in or subtract, I should say, the matrix elements to make them all stochastic. So we just call this the shift. So two different proposals to associate a non-stochastic Hamiltonian with a stochastic one. And we basically find a similar result, that the fraction of non-stochastic winds stays very small. And then you might ask, well, what if this is just a feature of the spectral gap? What if we can get around this by looking at the overall time to solution in a mode that allows us to proceed faster with a shorter anneal time than a purely adiabatic mode? So that's what this column corresponds to. So here's the designed case and the shifted case. And again, we're just kind of always seeing a small fraction. And in fact, it's an even more clear decrease with system size in the TTS case. So we would have liked to see a change with system size here, but we weren't able to access that scaling. But it's kind of what we would expect, that as you go out to large qubit number, this fraction of winds might decay. Okay, so those are the main technical results I wanted to communicate. So now I want to make some higher level remarks that also relate to the perspectives paper that I wrote with Daniel. So, you know, non-stochastic Hamiltonians, I would say, were one of the last great hopes for this original proposal of adiabatic optimization to achieve some kind of drastic speed up. And so I think that there's a bit of a cautionary tale here about equivocating hardness of classical simulation with useful algorithmic enhancement, you know, which is what's going on in quantum supremacy. But of course, non-stochastic interactions could be useful for many things. So they're crucial for universal AQC. They could be used for adiabatic quantum simulation, and they can be used within Hamiltonian error suppression. And since our designed Hamiltonians contain multi-spin stochastic interactions, minus XX, minus XXX, etc., the experimental progress on those still has great value. But you know, still the experimental challenges in, so if you like, you know, to borrow Jamie Kerman's term, full static emulation of a vector spin 1/2 qubit, i.e. all possible two local interactions, that's been experimentally challenging. So this led us to conclude in the perspectives paper that diabatic quantum annealing is perhaps the best path forward for near-term optimization in analog systems. So one reason to continue pursuing analog optimization is that if you look at it carefully, the overhead of gate model fault tolerance can easily consume the mild polynomial advantage of algorithms like Grover or amplitude amplification when it comes to a real finite application scale. So the idea of getting a quantum advantage from a fault-tolerant gate model computer just because we have some polynomial speedups with these algorithms is not a slam dunk just because we aren't really in the n goes to infinity limit, but we're capped at some finite application scale. And so because of that, you know, we need to explore these alternatives. We can't just say that, that it's all going to be gate model fault tolerance one day. because it's not clear that there's an advantage there. So that's discussed a bit in this work. But I also want to kind of take a step back and say, you know, what should we think about as theorists in this new field of heuristic quantum optimization? So I'm fully excited for the next round of hardware development and benchmarking studies. But as we heard, you know, in say Eleanor's talk, how, you know, part of the idea of heuristics is that you just want to build the thing and try them. So how should theoretical researchers contribute to these heuristics? I think that the connections between DQA and QAOA are an exciting recent development. But you know, we're currently kind of in an era where there's a gold rush of researchers proposing these heuristic methods as fast as they can write the papers. You know, act now to claim your own variational quantum circuit ansatz. So as theorists, I think what we should do is look at the bigger picture and try to address these algorithms that are just popping up over and over in a general way. And so recent work that applied a really general perspective to rule out quantum advantage in extremely noisy devices is this paper that many of you may have seen on the archive. And I think it's admirable in the sense that it takes on a large general class of algorithms. In terms of the specific result, I would say it applies to the extremely noisy regime. And in fact, the classical competing algorithms in this work are sort of directly related to the high temperature simulation results. So you could think of what they're simulating, you know, is so high temperature, so noisy, that you're almost just guessing random strings. But anyway, I like this work because it's very general at addressing these algorithms. Something I just want to point out is that, you know, in this community, we seem to be fixated on using the problem Hamiltonian as a phase separation operator, right? And so maybe that's the right general class of algorithms to address, or maybe we should start thinking outside of that box, right? So here in the context of quantum annealing, I'm thinking that if you trotterize the evolution, you're really just inserting the problem Hamiltonian through this phase separation operator. And, you know, in a way, this is a really simple idea. It's almost the simplest way you could think of plugging the cost function into your quantum algorithm. But if you look at classical algorithms like branch and bound or simulated annealing, you know, they involve these more complex primitives, adaptivity, examining clauses one by one, and so on. So I think, you know, it's time for us to evaluate this general idea. That's at least one thought I want to share. And then the very last thing is just that we are looking for postdocs at the University of New Mexico. So we have a bunch of recent new faculty. You may recognize myself, Tamim, Milad. We have a bustling center for quantum information and control. Our postdoctoral fellows can work with any of our faculty or pursue their own research interest, and deadline soon, and you could start soon. So contact me if you'd like more information on that. And with that, I'll end. Thank you.
Thank you, Elizabeth, for a clear talk. So we can now accept questions from the audience or other speakers. Do you have any? May I myself ask a question? You compared non-stochastic Hamiltonian with its counterpart, designed counterpart. And how about the comparison between the simple minus x term with with Hamiltonian, in which we have plus or minus xx term? Is the designed Hamiltonian better in some sense than the simple generic, simple original vanilla transverse field Ising model?
Yes, I would say that we have good evidence that including multi-spin interactions, to the extent that it's experimentally feasible, seems to give a nice general improvement. It's not clear how much that extends asymptotically, but at least from a very simple perspective, you know, you can think of kind of from a classical random walk perspective, you're allowing yourself to flip 2 bits at a time instead of just one. So we did not study that systematically, but I would say my overall impression is that multi-spin interactions, just based on the literature over the years, seem to be worth looking at, yes.
Okay. So it's true both theoretically and experimentally, of course.
Sure.
So, okay, Daniel, do you have a question to ask?
Yes, I do. So Elizabeth, as you pointed out, there are at least two ways to design a Hamiltonian, by doing the L1 norm with a minus sign or by shifting. But of course, there are actually infinitely many ways to do it. You could have done the L2 norm, squaring every matrix element and putting a minus sign in front of it. So how can we be sure that there isn't some other way to do the designing that will suddenly give us a large non-stochastic advantage?
Well, let's see. So in a way, I mean, if you take the perspective that stochastic Hamiltonians are easier to build, then if you can find some designing prescription that gives you a stochastic Hamiltonian with a bigger gap, then you may as well look at that one. But it's a good question to consider these alternative approaches. You can see that at many points in our numerics, we were indecisive, that we realized that there were many proposals one could consider. And I think somehow, like if you look at the random matrix argument, in a way that was comparing one ensemble to another more than it was comparing each Hamiltonian directly to its counterpart. And it was just the fact that these ensembles kind of concentrated on certain properties, concentration of measure on certain properties. I would say that the random matrix theory argument indicates that no matter what prescription you use for designing, you'll see this basic tendency. But maybe that is too wildly inductive. I mean, I encourage people to look into it. It's really a question of where do you start to branch and bound all the different possibilities for how you might design.
I guess I misstated my question. What I wanted to really ask was not about designing, but let's call it signing. So suppose you start from a stochastic Hamiltonian, and you try to do the opposite of what you did, and you try to introduce sign. So what you've shown is that if you use the shifting or the L1 norm trick, that wouldn't help.
Right.
But there might be other ways that you could take a stochastic Hamiltonian and introduce signs into it such that it will help.
Absolutely. And I think the fact that we have examples like the Pspin model shows that non-stochastic enhancement is possible, right? And it's just a matter of we need a better understanding of what makes those examples work, and can we generalize them to all problems? And so really this only indicates that doing something at random is not advantageous, but it doesn't mean we should stop looking for intelligent ways to add in non-stochastic terms. It's just that we can't kind of hope for a free lunch, I guess.
Okay. Any other questions? Okay. If not, okay, thank you, Professor Carson, and we can go on to the next speaker, Professor Tom Rosenberg, the president of Caltech, and thank you for coming here during a busy schedule. So please start the presentation.
Yes. Very good. Do you see that?
Yes.
That's good. I don't seem to have mine. There we go. Very good. So thank you so much for inviting me. It's really a great pleasure to be here. And I hope that my talk will both look backwards and point a bit to the future. What I want to talk about is an experimental realization of the Ising model in transverse field, motivated, as many of us have been, by the hope that you can do optimization problems more quickly or more effectively via tunneling, with applications across a broad spectrum of physical systems. I will concentrate on magnets, and in fact, what I want to do is tell you about the first experimental demonstration of quantum speedup in a quantum annealing versus classical annealing experiment. And this was in the disordered ferromagnet. But these experiments are a little old, and they've motivated a number of different approaches. And I want to tell you about the more recent work in the second strand of the talk, which is to talk about nonlinear dynamics of coherent spin clusters in the more dilute limit, where we have the hope of encoding information. So let me start with some additional motivation. If you haven't seen this quote from Richard Feynman, it's a wonderful one. I'm not happy with all the analysis that go with just the classical theory, because nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And so this attraction of a difficult problem that's meaningful, and also one that then lets your imagination run wild about opportunities, has been a powerful impetus to the field. It, of course, led Feynman to talk about what a quantum computer would look like. And here's the process flow chart, if you will. You take some input, you look at some combination of classical or quantum processes, perhaps comparing them. You then crunch the wave function, look at the output, and print out your result. So I'm going to tell you about an experiment that's very similar to this on a physical system. The physical system is a dipolar coupled magnet, lithium, holmium, yttrium tetrafluoride. I will describe the properties of this material system shortly. But basically, you have an initial wave function, initial state. Say that you're in the paramagnet. You quench down into the ferromagnet, either through a classical annealing or quantum annealing protocol. And then you look at what the final state is, the final state wave function. And you do that through a measurement experimentally of the AC magnetic susceptibility. So this is what the material looks like. They're beautiful single crystals. You can buy them in sizes up to centimeters because they're used as laser rods. When they're used as laser rods, they have a large mixture of rare earths, and then you get a lot of protected levels and all. We're interested in just one rare earth, that is the holmium, which is held in the lithium tetrafluoride matrix. And you can do substitution by yttrium. Yttrium is non-magnetic, and that then allows you to tune the energetics of the system, and in fact, the ground state. So this is a less pretty picture of lithium, holmium, yttrium tetrafluoride, but it shows you the crystal structure. The crystal structure is a body-centered tetragonal system. The red dots, I've just shown you the magnetic sites. That's where the holmium, or substitutionally the yttrium, fits. An important part of this is because of the crystal fields. This is an Ising system. So the spins point up along the C-axis. That's the Ising axis here, along here. And the spins are dipolar coupled. Okay, so it's a long-range interacting system. So if you have a pure system, that is all the sites are occupied by holmium, lithium, holmium tetrafluoride, then it's not obvious from the beginning what the ground state should be because of the dipolar interaction admitting both ferromagnetic and antiferromagnetic interactions. So of course, two dipoles like this on top of each other order ferromagnetically, two dipoles like this order antiferromagnetically. But it was shown many years ago by Ludinger and Tizza that basically the first nearest neighbor, which is here, dominates the ground state. So this is a ferromagnet. The first nearest neighbor coupling is ferromagnetic. Second nearest neighbor is antiferromagnetic. But the problem we will have is we're going to have a mix of ferromagnetic and antiferromagnetic bonds competing. So the Curie temperature of this material is 1.53 Kelvin. It's low because it's dipolar. So if it were an exchange coupled magnet, you'd expect to see something, say, of order 1,000 Kelvin. So as you dilute now, substitutionally replacing the holmium, the dipole concentration, with yttrium, which is non-magnetic, you still wind up with a ferromagnetic state, but you get some glassiness because of this competition between the ferromagnetism and the antiferromagnetism. And the Curie temperature just goes linear. It's a 1 over r cubed interaction in three-dimensional space. If you go farther down, then the sufficient disorder and the competition between the bonds gives you a spin glass state. And when you go even more dilute, you get into a state where you have short range correlations, but no ordering. And I'm going to spend today this evening, talking about the glassy ferromagnet, that's the optimization measurement, and then the spin liquid, which is the measurement which talks about disparate spin clusters that can encode information. Okay, so let me talk about a transverse field here and what it does. This is the Ising model and transverse field. So for this system, you have a ground state doublet, right? The energy is the same for all spins pointing up, all spins pointing down. The first excited state is 9.4 Kelvin above. I'll be talking about measurements that are done in the millikelvin regime. So there are essentially no excitations, thermal excitations up to the first excited state. However, if you put on a transverse field, remember I told you that the spins can't follow the transverse field to the Ising axis because of the crystal fields in the material. What it does is it mixes the doublet of the ground state doublet with the first excited state and splits the ground state doublet. And now I have an admixture of spin up and spin down that's proportional to this knob that I have in the laboratory, this transverse field. Another way of talking about this, of course, is that the Hamiltonian, this is just the dipolar coupling, Jij, these are Pauli spin matrices, commutes with sigma z until you put on a transverse field. And once it no longer commutes, then of course you get quantum fluctuations that depend on the strength of the transverse field. Okay, so you can see this. So here's an experiment that demonstrates this quantum speed up. What I'm plotting here is the imaginary part of the susceptibility. So this is the dissipation versus log frequency. So this is over 6 decades in frequency. So remember I said we're going to do AC magnetic susceptibility. We twiddle at a certain frequency. We ask what's the response. And so you see here with 0 transverse field, a usual sort of response. This is actually for a spin glass system with a temperature about 30 millikelvin or 40 millikelvin above the spin glass transition temperature. You see a broad spectrum like this. It's about 3 orders of magnitude, almost 3 orders of magnitude, full width, half maximum. If this were a single spin, you would see 1.14 decades, the so-called Debye relaxation. Now, as I put on the transverse field, and this is 8 kilogauss of transverse field, the gamma and the Hamiltonian, which is in Kelvin, goes as the square of the applied transverse field of the lab, you see that the frequency response moves up and up in frequency. So the peak frequency here goes from maybe a little over 10 hertz up to 10 to the 4th or a little over 10 to the 4th hertz. Now, the interesting part of this that you can see of how this is working, and that's really quantum, largely quantum, is if I take these curves now and I scale them on top of each other. So the next graph I'm going to show you is the scale by the peak frequency of each of these, and then the maximum. Okay, so that's this plot here. What you see is that this is the peak frequency being 1. And now on the high side, the fast relaxation, basically they all look the same. But as I change transverse field from 0 kilogauss up to 8, these long time, low frequency tails are pulled in. They're pulled in and cut off because there's tunneling through the free energy surface. Okay, so that's the effect of that. This is the experimental setup. We're going to take the material, we're going to mount it with its Ising axis along here, along the sapphire rod. We're going to have a AC susceptibility measurement with these coils that are wrapped around the crystal. The sapphire rods are for thermal heat sinking. And then we're going to put the transverse field perpendicular to the Ising axis, where we have another set of magnets to compensate for any misalignment of the transverse field. So we can make sure that there's no DC longitudinal field, which would just suppress the response and be uninteresting. Okay, so the experiment goes as follows. This is the phase diagram of the lithium holmium yttrium tetrafluoride crystal with 44% of the sites occupied by dipoles. You can see this is the classical transition. This is just 44% of 1.53 Kelvin. You see that as I apply a transverse field, and now I'm putting the transverse field in here in terms of the magnetic field, not gamma, but you can plot it either way. You see that I suppress the transition temperature to lower temperature. And then when I reach a critical value of the transverse field, I kill the ferromagnetism. So this is the quantum phase transition. This is the classical phase transition. We've spent time looking at critical exponents and all, and it's not quite like liquid helium where you can get 7 orders of magnitude, but we can get 5 orders of magnitude in terms of the critical behavior. In any case, what I want to do is I want to compare different cooling protocols. So I'm going to call the blue one here classical in the sense that I'm going to cool down only with temperature, no extrinsic tunneling from the transverse field. And then only at the end, when I get to whatever low temperature I'm at, I'm going to raise the transverse field to a certain level here at point C. Alternatively, I can do the quantum annealing. That is, I can cool down, if you will, with a large transverse field on, so lots of tunneling. And then I'm going to come down and turn off the transverse field and come into the ferromagnetic state. And I'm going to come to the same point C. And my question will be, do I get to the same physical state? And how fast do I get there? And I'm going to do that for a number of different points. I'm going to look just inside the phase boundary. I'm going to look a little deeper. I'm going to look very deep in the phase boundary at 30 millikelvin. And then I'm going to look in the paramagnet for a sanity check. Okay, so that's what you're seeing here. Point A is just inside the phase boundary where I have lots of thermal fluctuations. And you can see there's not much change. What I'm plotting here now is the real part of the susceptibility rather than the imaginary part of the susceptibility, because I know that the ground state here is a divergence of this real part of the susceptibility. This is as a function of frequency again now from 1 hertz up to 10 to the 4th hertz. It doesn't go there immediately. It takes time to diverge because of the competition between the ferromagnetic and anti-ferromagnetic bonds. So it's a little glassy in that sense. As I go a little deeper into the state, then I start seeing, I start seeing a difference between the quantum in red and the classical, but not much. They look basically the same. As I go deep into the ferromagnetic state, what you see is the two curves start separating And the onset of the behavior, the onset of the response to this AC magnetic field starts occurring at much higher frequencies. And this is the quantum speed up. I'll talk about that in a second. We'll focus on that. And then just to convince you that there's real physics to this, if you go back into the paramagnet, there's no difference between the two, even though there's a large transverse field on. Okay. So this is the quantum speed up. What you see is that you're getting into a different physical state as characterized by the real part of the susceptibility. That was the crunching at the end of this Feynman process, if you will. You see that this lower state has a much higher susceptibility, so it's approaching the divergence. It doesn't actually diverge because there are Dmag factors here because it's not a perfect needle. And the onset occurs at about a factor of 30 times larger in frequency than when I do this classically. And this is so-called F0 that I'm going to come back to. These are the most weakly pinned domain walls when they start moving, okay? Because of course I have a bunch of domains and I want to flip them to get the alignment and the net magnetization and the divergence of the susceptibility as I'm entering into the ferromagnetic state, okay? Now I've given you a lot of heuristics. I don't know if you can read the caption here. It says it appears to be some kind of wireless technology. So let me tell you about the wires, okay? What's going on microscopically. And the lithium holmium tetrafluoride system is beautiful that way because you really do know all the microscopic parameters. And so here are the numbers, if you will. So this is this F0, the most weakly pinned domain wall. And I'm looking at it as a function of 1 over T. So on the left here, towards 0 is high temperature. To the right is low temperature. Obviously, I'm picking 1 over T, log F0 versus 1 over T, because in the classical limit here, I expect Arrhenius behavior, which is a straight line. And now what I can do is I can look at a series of different transverse fields. Remember, I have a quantum parameter now. So a lot of experiments on magnets, quantum magnets, depend on the fact that you go athermal at the lowest temperatures. There's no longer a thermal temperature dependence. And you say, well, that means I must be quantum. But of course, you could just be thermally decoupled. Here, we have the ability to manifestly put in the quantum mechanics and look at a series of different transverse fields indicated now by gamma. And you know that even though over this whole range, it's flat here, it's athermal, that the phase diagram, the gamma T phase diagram, continues to evolve throughout this region. So you know the system's responding. So this is a real indication of being dominated by a quantum process rather than a thermal process. And so what you can do now is you can take slices as a function of the quantum knob in the different regimes, okay? And what we do is we then map it just onto a simple particle quantum tunneling model, where now the particle is the domain wall and the barrier is really the bunch of spins that are pointed in the opposite direction. And we just use a WKB approximation. And when we solve for that, we can actually, the solid lines here are a fit to this thermal plus quantum channels, where we assume they just work in parallel. And then we can solve for the mass of the domain wall, basically the number of spins. And we find that roughly 10 spins are tunneling at once. So the quantum speed up comes from the fact that if I have two domains here, the green one's down, separated by an up domain, if I want to now get closer to the ordered ferromagnet, I classically flip each of these spins one at a time. But quantum mechanically, I can get a response on the nanometer scale with roughly 10 spins flipping at once from our fit. So that's the origin then of the quantum speed up here. Now this led to a number, and this is old work. I know that, and I've learned in this conference already, a lot of more modern work. One of the first simulations here that came out a couple of years after our experiments where Santaro et al., Roberto Carr's group, with an 80 by 80 disordered 2D Ising model. And you can see here they did basically a classical number of Monte Carlo steps. This is the ground state energy. You wind up with the classical annealing result compared to the quantum annealing. You see the quantum speed up, although this is a 2D system. You do not see, however, you still see a power law dependence. Yeah. And of course, more recently, experimentally, there have been much more elegant, programmable opportunities for doing quantum annealing. The DWave system, probably the most famous out there. I know all of you have seen these kinds of graphs where you have the qubits that are tightly connected within a unit cell with certain sorts of connections to other unit cells. Of course, this is one of the older designs. The new designs have many more connections. But the point I wanted to make is that you can program in the problem. Our system, of course, well, it was 10 to the 23rd spin, so it was certainly macroscopic in that way. But it solved its own problem. It found what its ground state was. It didn't really care what you wanted to tell it, to what problem you wanted to solve. Of course, we have some ability here to do that, but these curves with the usual annealing functions here look very similar to the kind of protocols that I was showing you before. Now, there are questions, of course, of whether these superconducting Josephson junctions, how long their coherence goes over this time. But I think it's really demonstrates the progress that's been made in the field, which is as much quantum engineering as quantum science. So let me move on now to somewhat more modern work. And the motivation for this is the comparison to this notion of only being able to solve the problem the system wants to solve versus being able to program in the problem that you want to solve. And to do that, we're using the same system, the lithium holmium yttrium tetrafluoride system, but in the limit of only a few % of the sites being occupied by spins. And this spin liquid, if you will, is very interesting because it has good collective behavior. Basically, it forms isolated spin clusters that can be labeled by frequency, and I'll show you how. And they're competing ground states, of course, which I won't talk about here, but we've done a fair amount of work on. What I'm interested in telling you about, though, is our work using nonlinear dynamics. And by driving the system nonlinearly, we're able to encode information. We have collective excitations that can have coherence times, which are tens of seconds. And there's extreme sensitivity to what the ground state is. So what do I mean by a spin liquid? I'm going to use it in the sense that there's no long range order as the temperature goes to 0. The spins are not frozen. The fluctuations persist. And in fact, those fluctuations are quantum in the case of lithium holmium yttrium tetrafluoride. Their origin is that if you think of the dipolar interaction, if I have a concentrated sample, then the transverse component of the dipolar interaction, remember the dipolar interaction looks like a butterfly, the transverse component of the dipolar interaction cancels in the concentrated case. So if I have a spin here, its transverse component is canceled by the spin on the other side. However, if I now dilute it, I wind up with many spins that do not have compensation. So I have effectively an internal transverse field of order kilogauss that gives you just by dint of disorder the quantum fluctuations. And it's not a simple paramagnet because there's short range correlations in this material. So you get collective behavior. So of course, the notion of spin liquids has been studied. There are many lower dimensional systems which show really profound effects. You can get the freezing prevented by the quantum fluctuations, which is what I'm going to talk about today in terms of lithium holmium yttrium tetrafluoride with 4% of the sites occupied. But you also can have geometric frustration and, of course, amplification of fluctuations with reduced dimensionality. We've done some work on the gadolinium gallium garnet, which shows similar effects, but I won't show them here today. So what does the spin liquid look like? I showed you the spectral response before of the spin glass. And in a lot of ways, this is the anti-spin glass. So what you're looking at here, and I'll explain what I mean by that. What you're looking at here is the real part of the susceptibility at a series of temperatures, 0.18 Kelvin down to 50 millikelvin, 180 millikelvin to 50 millikelvin. And then on the same plot from 10 to minus 1 hertz to 10 to 3 hertz, the imaginary part of the susceptibility. And these contain the same information. They're related by the Kramers-Kronig relationship. But you can see things a little easier on the imaginary part of the susceptibility. One thing you note is as you go from high temperature to low temperature, the system slows down, it moves to lower frequency. If this were spin glass, what you would see is you would see that this spectrum here, which is about 2 decades wide, so larger than Debye, telling you there's more than one spin doing anything, it would broaden out. Okay, it would get broader and broader and broader as the spin clusters start to freeze in the spin glass. Here, as you see, it's doing the opposite. The spectrum is narrowing, and I'm going to do the same trick. I'm going to look at the imaginary part of the susceptibility. I'm going to plot these on top of each other, normalizing by the peak frequency and the peak height. Okay, and so what you see here is that those same curves coming on top of each other. And now, as I go from higher temperature, the purple, to the lower temperature, the 50 millikelvin, in fact, it almost looks like a gap opens up. The distribution, the spectrum narrows. In fact, it narrows at the lowest temperatures to a full width half maximum, which is narrower than Debye. So it's no longer a relaxational spectrum, right? You can't have less than one spin participating in this. What it tells you is really you should start thinking about this like 2-level systems, okay? And so if you imagine a system, a 2-level system, one way to probe it is with pump probe spectroscopy. So if you look, or if you think of an ion, you do that. This is not an optical experiment. This is a magnetic experiment. I want to be clear about that, but it's analogous to pump probe and optical bleaching. We're going to burn holes in the spectrum by exciting these clusters, these 2-level systems, which are spin clusters, which are effectively composed of a few hundred spins from their ground state into their excited state. And so how you do this is you use a small amplitude excitation to measure the equilibrium property, and then you fix a frequency at F0 and you excite the nonlinear response. And to give you an idea of the kind of energies you're talking about, you're only talking about a Gauss or an Oersted excitation amplitude. So you're not talking about very much magnetic field, but it's enough to burn a hole. So this is about half a Gauss. You can see the nonlinear susceptibility. This is the imaginary part on the top, the real part on the bottom. What you see is basically the hole in the spectrum. The hole in the spectrum can be fit by a phonoform, which means there's coherent scattering between the 2-level system and the continuum. And this is the phonoform. I don't want to go through that. This, of course, was developed for atoms by Ugo Fano, talking about the interference, quantum interference between excitations inside the ion and then full ionization of the atom. And there are 2 parameters here which I want to point out to you. One is the line width, that's the gamma. The other is the Fano asymmetry parameter Q, small q. Okay. So this is our picture. We have these spin clusters. You can label them by frequency in the sense that if I drive this at different frequencies, I pick out different size spin clusters. And then I can excite them out of their ground state, which gives you the hole because they're no longer responding, okay, when I'm twiddling them with that small field. So I have this excitation spectrum. And they're interacting with other excited clusters, but they're also interacting with non-resonantly excited clusters that are close by. So I have excitations up into the higher state, energy state, which tends to be more fully magnetized, and then various pathways that they can relax. And it's the coherence then and the interference between these pathways that gives you the Fano line shape. Okay, so let's look at this resonance and understand how it's developing. What I'm trying to get to is to understand what this state is. What are these nonlinear excitations and how can we tune them? And in fact, can we isolate them from their environment so you might start thinking of them like quantum bits? Okay, so here is at low temperature, 110 millikelvin, the imaginary part of the susceptibility versus delta F, which is now the, it's the difference in frequency between the drive frequency that's exciting them and looking about them. And you see here, you get a nice Fano line shape as I increase the temperature, and this goes up to 700 millikelvin. The line shape basically broadens until at the highest temperature, I've effectively melted the clusters. So I've just driven them apart. Their binding energy is such that that's not going to be able to sustain those high temperatures. The line width is gamma in the Fano form is basically Arrhenius. Okay, so I'm just having a thermal excitation process. And then you can see what the Fano parameter Q is doing. That at low temperatures, basically, it's some mix of these different pathways. As I raise temperature, then I'm exciting more of these clusters. I'm flipping basically anti-ferromagnetic bonds to ferromagnetic bonds. The clusters start revealing themselves to each other and start interacting. And I wind up at one limit of Q. Q goes from 1 to -1. So I'm getting close to one of the limits where it's really the interactions between the clusters themselves that are dominating. And there's not much quantum interference left. Okay, so this tells you something about the system and the energy scales in the system. It's not terribly useful otherwise. However, remember, we have a transverse field. And you can also tune this resonance by applying a transverse field. Remind you of the Hamiltonian here, where this gamma, so I'm sorry, the gamma here is the transverse field, not the line width in the Fano resonance. I apologize, I should have changed that. So here you see a sequence of Fano resonances at a series of transverse fields from 2.5 kilogauss to 5 kilogauss. Now, let me point out a couple of things. One is if I look at one limit, say the 2.5 kilogauss limit, I have a asymmetry about 0 as I move off from the drive frequency. That tells you Q is in one limit. Remember, it goes from -1 to +1. We call this greater than 0. That's sort of arbitrary. But at the highest transverse field, I've gone to Q less than 0, okay? Because it's now on the other side of 0, the asymmetry. And so somewhere in between 2.5 and 5, I'm basically going to get to Q goes to 0. So I'm shifting the energetics and the coupling of the spin clusters. The Fano parameter Q being 0 is interesting because that's where you basically decouple from your environment. That's what it means. There's no interference between those paths. There's no more response to the external field, okay? And you can see that happens around 3.5 kilogauss here. The other thing I want to point out is you remember when we just did temperature, the major effect was to broaden the line shape, right? We were melting it, we were smearing it. You can see here, as you move the transverse field, the line width stays very sharp. So there's no broadening here. There's no thermal effect. So this is purely a quantum mechanical effect. And so this is Q mapped out for a series of transverse fields. I just picked out those demonstration plots to show you the evolution. It effectively seems to go roughly linearly. through 0 with 0 at about 3.5 kilogauss. And I discuss this in a little more detail in a second. Okay, so what have we found out in tuning this resonance with the transverse field, the phonoresonance with the transverse field in these isolated spin clusters? The line width stays constant, so as the quantum tunneling rate increases, so that's good. We can deconvolute thermal and quantum effects. I haven't showed you here, but it has a long lifetime. In fact, the quality factor, capital Q, and I'll show you that, is effectively independent of transverse field, is something of the order of 10 to the 5th. So it's the frequency we're driving these things at, which is say 100 hertz, versus the millihertz line width of this system. You can see this is now a summary of all that data as a function of transverse field, where you're moving from one side of 0 to the other, and you can see the sharpness of this response. So there's weak coupling to the environment because of this large quality factor. And there's no interference then as Q goes to 0. So if there's no interference, the prediction is then that there should be no dissipation. Now remember, we're measuring the imaginary part of the susceptibility, which is a measurement of the dissipation. So what does the imaginary part look like in the nonlinear regime? Okay, so that's what I'm going to plot here. So here, let me just show you this is the Q factor, the quality factor. Okay, so basically of the resonance, which is of order 100,000. So it's a very sharp resonance. This is the phono Q asymmetry parameter, small q, which I showed you before. And down here, I'm looking at the phase. The phase is the ratio of the imaginary to the real part of the susceptibility. So when the imaginary part of the susceptibility goes to 0, phi goes to 0. And what you see is if you look at the nonlinear response, it varies smoothly. I'm sorry, the linear response varies smoothly. That's the red here. But if you look at the nonlinear response, in fact, the dissipation goes to 0 just where the quality, just where the phono parameter crosses 0. Okay, so the fact that you're decoupling from the world, that these are localized states that can be tunably isolated from their environment, is borne out by the measurements of the global susceptibility. So the hope, of course, is that then one can use tune this system, these spin clusters, which are now labeled by frequencies, to decouple from their environment and then excite a multitude of spin clusters of different frequencies and then mix them, which would be the computation. We've not done that yet. Okay, let me note that this actually, you can also tune with pump amplitude. So the pump amplitude, of course, drives the system harder, will flip some spins. We see here also that Q crosses through 0. This is the phono Q. As a function of pump frequency, this is from 0.3 of a Gauss up to roughly 0.6 of a Gauss. Here the line shapes, but note that this is not as clean an experiment. I mean, there's probably interesting physics in this, but it's harder to deconvolute effects because see how narrow or reasonably narrow at 0.3 of a Gauss this response is, and by 0.5 of a Gauss, you've already broadened this out. It's because you're heating it. There's eddy current heating in the material's an insulator, but there's metal all around. So we can work on reducing the thermal mixing, but it's hard. So the transverse field is a much better tuning parameter. Okay, so let me conclude. This is lithium homium yttrium tetrafluoride. It's an experimental realization of the Ising model in transverse field. You can look in different regimes. I've told you about 2 of them. One is the disordered ferromagnet. And here the quantum annealing gets you to the global ground state much faster. And we can microscopically model this and tell you about the domain wall tunneling in a quantitative fashion. And in the spin liquid, you get these nonlinear excitations that create basically emergent degrees of freedom. They're long-lived, they're otherwise inaccessible, and we're now at the point of seeing if we can manipulate them in a way that would be interesting. I think the quantum dynamics of them is interesting in itself, but whether they can be used for mixing would be, of course, is another interesting question. So here, this is what I always tell my students, stick to it. There's a future in cryogenics. And this work has been done over the years with a number of very talented graduate students, David Bitko, Justin Brooks, Cy Ghosh, Michael Schmidt, Dan Silovich, who's a research professor at Caltech now, and my current student, Chris Tang, Wenhao Wu, who's at Texas A&M, both when I was at U Chicago, and I've been at Caltech now for 6 years. And all this work has been done with Gabe Epley at ETH. And I won't give you all the old references. If you're interested, please, you can find them under these guys' names. But this is a more recent reference about the high Q nonlinear dynamics that came out last year. So thank you very much for your attention. I appreciate the opportunity to let you know about this, and I will stop sharing.
Thank you very much, Professor Rosenberg. Very interesting talk, indeed. So there's a question from the audience. Let me read it. Thank you for your lecture. Do you think quantum tunneling always exists in this problem setting with connection of quantum fluctuation, or on the special circumstances, only quantum tunneling exists? Well,
so I think that once you put on a transverse field, it has two effects. In the pure system, it's the quantum tunneling I was telling you about. It also, this is also the random field Ising model. And so you can, in fact, for small transverse fields, you increase the random field pinning. And for large transverse fields, you then see the tunneling and the quantum speed up in the ground state and the domains. And we've done a number of experiments showing that. There's a Nature paper a little while ago that looks at the competition between the random field effects and the quantum tunneling. In the disordered material, very dilute, there are intrinsic quantum fluctuations or quantum tunneling, as I was saying, because of the dipolar interaction being unbalanced. And so, yes, in that case, there's always quantum tunneling. In the pure case, in the classical, at high temperatures, there's probably very little quantum tunneling. One experiment we're doing now, which is kind of fun, is to look at Barkhausen noise in the ferromagnet with the transverse field. So there's been a lot of work, of course, done on the sorts of Barkhausen effects when you just ramp the field around a hysteresis loop, and then you get avalanche behavior of the domains. But as far as we know, nobody's done that in the quantum limits. So we want to look at what quantum Barkhausen looks like. And there we'll be able also to say a lot about what does the quantum tunneling look like, and what are the parameters that characterize it in both pure and disordered ferromagnets.
Okay, thank you. Any further questions from the audience? Daniel, Professor Leader, please.
Yeah, hi. Thanks for a great talk. And
thanks, Dan.
So you've shown all this remarkable evidence that this material is very quantum, so to speak, weakly coupled to the environment and so on. And it just begs the question of programmability of this material, which you mentioned in the beginning. And of course, it's not naturally a programmable material, but I was wondering if one can play tricks like introducing additional impurities that you'd be able to address, something like what's done in NV centers in diamond or phosphorus on silicon and so on.
Right. Yeah, I mean, it's a great suggestion. And actually, Gabriel's doing more in that regime. So you can imagine in a more dilute limit, putting other rare earths in, addressing them optically then to affect, say, the holmium spin, and being able to control its state, and then looking at the interaction between the holmium spins where the accessibility is versus, I don't know, an STM or an optical probe or whatever it might be, to couple with the actual spins you want to interact. So I think there are opportunities that way. I think in the bulk material, it's pretty hard, except if we're hoping, as I mentioned, to, if you will, the self-segregation of these clusters to try to work around the fact that we can't actually address them spatially. We're addressing them in frequency space, so we can't do it in real space. But I think you're right. There are analogs to impurities in diamonds and so on and so forth. Yeah.
I see.
Yeah, it's a great point.
Thank you. Okay. Any further questions? Well, I myself, I'm Hidetoshi Nishimori from Tokyo Institute of Technology. I was very much impressed by your very early work, 1999, and
it's a while back, isn't
it? You established clearly that quantum effects have an advantage over classical thermal effects, but we theorists are still struggling to establish that theoretically. So in terms of the simple transverse field Ising model, as Professor Daniel Lieder talked yesterday or early this morning, and he said that simple transverse field Ising model using adiabatic process may not lead to a good amount of advantage over classical methods. So we still have done your homework in that sense. Do you have any suggestions for theorists or in any other respect?
No, I mean, what I've really enjoyed is the large amount of activity in this field. From what I've seen, I am somewhat pessimistic that one is going to really get breakthroughs. Clearly, you can get speed up, but if it's still power law, or or not much change in the power law, there are going to be limitations to its advantages. But one hopes by crafting, at least from an experimental point of view, crafting different experimental configurations with different drive parameters, that we can understand enough about the microscopics to shed some light on the kind of model systems that you and other theorists are using. So I'm optimistic about that portion. I have less to say about what a real quantum computer will look like.
Thank you very much.
Thank
you. We are just on time, and we thank all the speakers in this session. So this closes session 3 of this conference, and the next session, session 4, will start in 4 hours of time from now. Okay, let's see then. Bye now.